there is a special kind of silence found only in the aftermath of a dying star. A silence so deep it feels like the universe is holding its breath. When a giant sun collapses and leaves behind a core no larger than a city, something stranger than imagination is born. In that stillness, matter folds in on itself, light bends, and the cosmos reveals one of its most mysterious creations, the neutron star. Welcome to AstraFlow. Here, science drifts like starlight, and curiosity becomes calm. Tonight, let your thoughts slow down, your breathing find its rhythm, and your mind float through wonder. Before we begin, I'd love to know where you're listening from. Are you lying in bed under city lights, or watching the stars from somewhere quiet? Tell me in the comments. It's always peaceful to imagine the AstraFlow community scattered across the world, drifting together through the same sky. And if this calm journey brings you peace, you can gently support AstraFlow by liking this video or subscribing. It helps this little corner of the cosmos keep glowing. Now, let's begin tonight's voyage into the quiet story of the life of neutron stars, the strangest objects in space. The story begins with endings, with stars so large that they burn through their fuel in brief, brilliant lifetimes. When their light falters, gravity tightens its grip, and the core collapses at astonishing speed. Atoms shatter, electrons fall into protons, neutrons lock together in a dense, trembling mass. The collapse halts only when the pressure becomes almost unimaginable, a pressure so strong that an entire mountain could be crushed to the size of a grain of sand. In the calm of this moment, what remains is no ordinary remnant. A neutron star is both ghost and survivor, a memory of a once shining sun, and yet something wholly new. It spins, it hums, it holds the secrets of physics pushed to their extreme edges. And in the darkness, it emits a faint glow, like the lingering warmth of a final breath. As you lie back and let your breathing soften, imagine the universe stretching wide around you. Imagine drifting through the debris of a long-ago supernova, where dust moves with the slow grace of drifting snow. Imagine approaching a tiny star no bigger than a city, yet thousands of trillions of times denser than anything on Earth. Its gravity gently tugs at the surrounding space, subtly bending the paths of particles and light alike. Neutron stars exist in a realm where intuition fails and awe begins. They are the bridge between the known and the impossible, celestial puzzles that challenge our understanding of matter, time, and the limits of physics. Their surfaces tremble, their cores swirl like superfluids with no friction. Their magnetic fields twist space with forces beyond human comprehension. Tonight, we'll drift through their world in soft, steady steps. No rush, no urgency, just the slow unfolding of one of the universe's quietest marvels. You can let each idea wash over you like a tide, gentle, steady, rhythmic, carrying you deeper into rest as the cosmos opens its pages. So breathe in, breathe out, and let yourself begin to fall into the calm gravity of this story. The story of neutron stars, the strange survivors of stellar death. When we think of endings, we often imagine disappearance, a fading, a quiet dissolving into memory. But the universe thinks differently. In the vastness of space, endings rarely vanish. They transform, they compress, they take on new shapes and new meanings. And so, as we stand before the strange existence of neutron stars, a gentle question rises. What remains after great endings? What stays behind when something enormous, luminous, and ancient collapses into darkness? It's a question as old as the first humans who looked up at the night sky and wondered where the fallen stars go. Even now, with telescopes and equations and simulations, we still carry that quiet curiosity. We still look for continuity, the thread that ties one form of existence to the next. In the universe, that thread is everywhere. A dying star becomes a remnant becomes a force, and a force becomes a story written into the structure of space itself. So when a massive star reaches the end of its life, it doesn't simply stop. Instead, it transforms into something dense, small, and impossibly intense. A neutron star. A star that no longer shines, yet still influences the cosmos with a kind of soft, invisible gravity. It is an ending that becomes a beginning. A quiet survivor whispering the memory of what it once was. You might think of the way certain moments in your own life feel like collapse. Times when something bright burns out, when a chapter folds shut. And yet, often, what remains afterward is not emptiness, but a new form taking shape in the quiet. Something sturdier, smaller perhaps, but more concentrated, more essential. Almost like the way a collapsed star becomes dense enough to defy imagination. In the universe, destruction is rarely final. The collapse of a massive star is violent, yet from that violence comes something astonishingly calm. A neutron star spinning alone in the dark, humming with forces deeper than light. It is one of the clearest reminders that endings can be transformations, even if the transition is fierce. Neutron stars challenge the very idea of finality. They ask, what if endings are simply thresholds? What if the universe keeps everything but in new forms? These questions drift through the cosmos like soft echoes, inviting us to slow down and reconsider how change unfolds. Nothing is truly lost. It only becomes something else, compressed into a new shape. As you listen now, with your breath steady and your body growing heavier against your bed, imagine this idea settling gently around you. Imagine all the stars that have lived and died across the universe, each one leaving behind some trace, a ripple, a remnant, a fragment of light or gravity. Imagine that in the grand tapestry of existence, endings are woven right beside beginnings, so closely that the threads overlap. Neutron stars are reminders of this cosmic rhythm. They are the universe's quiet answer to loss. They say, even when a brilliant fire collapses, something extraordinary remains. And tonight, we will follow that thread through pressure, silence, collapse, and transformation to see what truly survives when a giant star's final light fades. Let that question drift with you now, like a feather caught in a slow breeze. What remains after great endings? As you breathe, let the curiosity settle softly, preparing you for the journey ahead. To understand neutron stars, we first drift back to the simple truth that stars are not eternal. Even the giants, those massive suns that outshine entire neighborhoods of the cosmos, live on borrowed time. They burn fast, they burn bright, and when their fuel runs thin, the delicate balance that held them steady begins to falter. Gravity, patient and persistent, takes over. The star collapses inward, folding into itself with unimaginable force. Yet what emerges from this collapse is not a ruin, not a scattered cloud of ash, but a stellar remnant, compact, concentrated, and deeply strange. A neutron star is a star reduced to its essence, every particle pressed against every other, every fragment of matter pushed into new forms by pressures we can barely imagine. In the quiet aftermath of the collapse, the chaos settles into order, dense, silent, and perfectly balanced. It is here, in this compressed core, that the universe reveals one of its most mysterious creations. A neutron star is small enough to hold in your mind, yet vast in the stories it carries. Imagine something no bigger than a city, perhaps 20 kilometers across, yet heavier than anything you have ever touched. Heavier than mountains, heavier than continents, heavier than all the people who have ever lived, combined. It is a contradiction wrapped in gravity. Small but immense, quiet but intense, dark but filled with invisible power. These remnants are incredibly varied. Some spin slowly, like a tired wheel coasting to rest. Others turn hundreds of times per second, faster than the blades of a hummingbird's wings. Some emit beams of radiation in perfect rhythm, creating cosmic pulses that sweep across space like the ticking of a celestial clock. Others glow softly in X-rays, revealing themselves only when matter falls onto them, releasing bursts of heat and light. And still others, the magnetaires, hold magnetic fields so strong they could erase the information on every credit card on Earth from halfway to the moon. Yet despite their extremes, neutron stars are astonishingly stable. They hold their shape through forces so intense that the crust is harder than diamond. Beneath that crust lies a sea of neutrons behaving like one vast superfluid, moving without friction, swirling in perfect silence. Even deeper, there may be layers of exotic matter scientists can only describe using equations and dreams, quarks dissolving, particles rearranging, new states of matter forming in a pressure cooker of cosmic proportions. All of this, the spin, the density, the gravity, the magnetism, is contained in a remnant left behind after a single star's death. A neutron star is not just an object, it is a process frozen in time, a memory of what came before, distilled into something new. As you breathe slowly, let this idea settle. The universe doesn't discard its creations, it transforms them, it compresses them, it finds new ways for them to exist. And in that transformation there is always something beautiful to notice, even in the smallest, densest, darkest stars. Tonight, we'll walk through their world step by step. Not to rush, not to understand everything at once, but to gently explore the edges of physics, where matter behaves like poetry and silence becomes a form of energy. Neutron stars are the universe's most patient storytellers. All we have to do is listen. Before a neutron star can exist, its parent star must undergo one of the most dramatic transitions in the universe, the inward collapse of a massive sun. Not a gentle folding, not a slow dimming, but a sudden surrender to gravity after millions of years of balance. For most of its life, the star held equilibrium, outward pressure from nuclear fusion pushing against the inward pull of gravity, like two hands pressed softly together. But when the fuel runs out, that symmetry falters. One hand pulls back, gravity wins. Imagine that moment. A star many times larger than our sun begins to fall inward, layer by layer, each shell collapsing onto the one beneath it. The outer layers plunge toward the core at a quarter of the speed of light. The pressure skyrockets. In the space of a heartbeat, the entire star compresses, as if the cosmos is drawing a long, sharp inhale. What had been enormous becomes impossibly small. Atoms themselves buckle under the weight. Electrons are forced into protons, forming neutrons. The star's core becomes a single, dense mass of neutron-rich matter, a kind of cosmic substance that doesn't exist anywhere else in the natural world. It is new, it is ancient, it is the result of gravity sculpting matter into its most compact form. In this moment of collapse, a profound silence settles over the star's interior. Even though the outer layers may explode outward in a brilliant supernova, the core remains calm, steady, almost contemplative. It holds, it endures, it becomes the foundation for a neutron star. If you imagine drifting near such a collapse, safely as a floating observer made only of thought, you would feel the space around you tighten. Gravity would grow sharp, almost tactile, as if the air itself were thickening. Light would bend, curving around the forming star as if pulled by invisible hands. The collapse is not just a change in size, it is a change in space-time itself. The creation of a neutron star is the universe demonstrating a truth it repeats again and again. Even under unimaginable pressure, something new can emerge. The star's collapse is not purely destructive. It is an act of transformation. From the ashes of a supernova, from the ruins of a giant, a small and astonishingly stable object is formed. Extreme gravity becomes structure. Chaos becomes order. As you lie here listening, with your breath soft and slow, you can imagine this collapse as a kind of cosmic exhale, the release of old light, the final breath of a once mighty sun. And in that release something enduring is born, something that will persist far longer than the light that came before it. For a moment, think of the strange balance in your own life, the way certain pressures shape you, the way change can compress experience into something more concentrated, more essential. A neutron star is the universe's reminder that collapse is not always destruction. Sometimes it is the beginning of a deeper form. Tonight, as we explore these stars step by step, this first transformation sets the tone. A giant falls inward, a core stabilizes, and a new kind of object, small, dense, humming with silent energy, begins its long life in the dark. Once the collapsing star reaches its limit, a new kind of matter forms, something so dense, so tightly packed, that it almost defies language. The core becomes a vast, trembling ocean of neutrons, each one pressed shoulder to shoulder with its neighbours, forming a substance that exists nowhere else in the natural universe. This is the neutron sea, silent, depthless, and utterly strange. To understand this ocean, imagine taking the entire mass of Mount Everest and compressing it into a single teaspoon. Even then, you would still fall short of the density inside a neutron star. Here, the atoms that once made up the star's core no longer behave like familiar building blocks. Their boundaries dissolve. Electrons are crushed into protons, becoming neutrons. Those neutrons merge into a collective identity, forming a fluid so dense that a single cubic centimetre could outweigh a fleet of ships. And yet, for all its intensity, the neutron sea is peaceful. There are no waves, no tides, no surface winds. Everything inside a neutron star is held still by gravity's unyielding embrace. The neutrons drift in a frictionless, deeply calm state, more like a dream than a fluid. If you could place a finger on this sea, which no human could ever do, you would not find water or rock. You would feel a kind of solidity that resists and yet flows, a paradox wrapped inside a single point. Drifting through this idea, imagine yourself floating above that sea, weightless and unhurried. The surface beneath you would be smooth, glowing faintly with trapped heat from the star's formation. It would feel ancient yet newborn, a relic of an explosion combined with the beginnings of a new cosmic chapter. Around you, space would warp subtly, bending ever so slightly toward the star's centre, as if even emptiness were leaning in to listen. Scientists describe this neutron matter using equations that stretch the imagination. Superfluidity, degeneracy pressure, quantum states layered on quantum states. But beneath all the terminology is a simple truth. Inside a neutron star, matter behaves like a single, collective organism. There are no isolated particles. Everything acts together. Everything moves as one. It is matter in its most unified form. And perhaps that unity is part of the star's calm. There is no chaos here. No molecular vibrations, no thermal noise bouncing between atoms. Instead, there is a profound stillness, a substance so quiet it makes even deep ocean trenches feel noisy by comparison. It is the closest nature comes to complete silence. In this part of the journey, you can let your thoughts settle like sediment drifting to the bottom of a tranquil sea. Let the density, the pressure, the stillness wash over you in soft, slow waves. The neutron sea is not merely a scientific concept. It is an invitation to imagine stillness beyond stillness, a silence so deep it feels infinite. As we continue, we'll explore what surrounds this sea, the crust that holds it in place, the magnetic storms above it, the spin that keeps the star in motion. But for now, let this ocean remain in your mind. Heavy, motionless, serene. A reminder that even the most extreme places in the universe can hold moments of extraordinary calm. One of the strangest truths about neutron stars is their size. After the violent collapse of a once giant sun, what remains is no larger than a city. 20 kilometers across, perhaps a little more, perhaps a little less. A cosmic core compressed into something that could fit inside the footprint of a small map. The universe takes a star that once spanned millions of kilometers and folds it down into a sphere you could, in theory, drive around in half an hour. In this contrast, there is a kind of quiet wonder. How can something so small contain so much? Imagine drifting towards such an object, gliding slowly through the dark. At first, it might appear almost modest, a faintly glowing sphere suspended in silence. No enormous corona, no sprawling magnetic loops like our sun, just a compact orb of extraordinary density. But as you approach, the scale shifts. The star's surface becomes a kind of cosmic terrain, smooth in places, jagged in others, shaped by forces so powerful that a mountain here rises only a few millimeters high. A bump the size of a grain of rice could outweigh a mountain range on Earth. Every feature on a neutron star is exaggerated by contrast. The crust, only centimeters thick, is harder than diamond. The ground beneath it is a sheet of nuclear matter dense enough to crush anything that touches it. The gravitational pull is so strong that if you somehow stood on the surface, protected by impossible technology, lifting your foot would require the strength of 1,000,000 lifetimes. A single step would feel like pressing against the entire weight of the Earth, and yet despite these extremes, a neutron star is incredibly stable. Its roundness is almost perfect. Its surface barely shifts or quakes except in rare star quakes. Brief, sharp adjustments where the crust cracks from stress and the star's rotation suddenly speeds up by a fraction. Even those tiny jolts ripple outward through space like whispers carried on a long-distance breeze. Let your mind wander for a moment. Picture a city at night. Quiet streets, dim lights, a hush that settles after the world goes to sleep. Now imagine the calm wrapped around a sphere of unimaginable density. That is a neutron star, a quiet, city-sized remnant shining faintly in the void. No atmosphere thick enough to scatter light, no winds to stir the surface, just a steady, unwavering glow, the after heat of collapse radiating softly into the dark. The compactness of neutron stars is more than a physical fact. It is a meditation on scale. The universe does not always express power through size. Sometimes it expresses it through concentration, through distillation, through reduction to the essential. A neutron star is the purest form of this, the core of a star compressed until only the strongest forces remain. As you rest here, breathing slowly, you might consider the ways your own experiences sometimes condense. How vast emotions contract into a single moment. How years of growth collect into a single decision. How everything complex can occasionally shrink into something simple, dense, and transformational. The universe mirrors these patterns, reminding us that small things can carry immense weight. In the cosmos, even mountains can be millimeters tall. Even giants can become tiny. And even tiny things can hold extraordinary power. The neutron star is proof of this, a city-sized world sculpted by gravity, glowing quietly in the deep silence of space. Gravity on a neutron star is not simply strong, it is absolute. It is the quiet, relentless force that shapes every atom, every ripple, every whisper of energy that drifts near the star's surface. After the collapse of a massive sun, gravity becomes the reigning architect, compressing matter until it teeters on the edge of possibility. On a neutron star, gravity is not just a physical pull, it is a presence, a soft but unyielding pressure that bends space, curves light, and holds the entire structure in perfect, unwavering stillness. Imagine floating far above such a star, gently drifting closer. You would never feel a sudden tug, never experience a violent pull. Instead, the star's gravity would feel like an invisible slope, a deep, quiet valley in the fabric of space. As you descend, the curvature grows sharper. Light begins to bend around the star, its path warping like a river flowing around a stone. Even photons, which normally rush straight and unimpeded, find their trajectory altered here. The neutron star's gravitational field is so intense that if you hover near its surface, you could look around and see the back of your own head, light curved full circle by the star's immense pull. If you stood on the surface, something no living thing could ever do, the force beneath your feet would be astonishing. You would weigh billions of times more than you do on Earth. A small object, no heavier than a paperclip, would crush the ground like a meteor. Gravity presses the star's crust into a perfect sphere, smoothing out any imperfections. Mountains can rise only millimeters before gravity flattens them. Even the most rigid materials exist here in surrender, and yet, for all its strength, this gravity is beautifully balanced. It holds the star together with unshakable calm. It stabilizes the neutron sea within, compressing every layer into harmony. There is no trembling here, no instability, only the quiet certainty of a force that has found its equilibrium. The entire star becomes a meditation on pressure, pressure so immense that matter itself rearranges into new forms, but from the outside all you would see is a serene sphere, glowing softly like a distant ember. Take a slow breath, letting your chest rise and fall. Picture the neutron star's gravity as a kind of cosmic grounding, a reminder of the forces that hold things in place, even when everything around them changes. This gravity isn't chaotic, it isn't violent, it is steady, ancient, patient, like the weight of a deep truth settling gently into your awareness. The curvature of space around a neutron star is so strong that even time behaves differently. Clocks at the surface run slower than clocks far away. A gentle stretch of moments, a soft elongation of now. To the star there is no hurry, no rush. Time flows in long, measured breaths, as if the universe is inhaling slowly and never fully exhaling. As you drift in your own stillness, imagine that slow time wrapping around you like a warm blanket. Gravity here is not a threat but an anchor, a force that holds the star together through eternity, an invisible hand resting calmly against the fabric of reality. Neutron stars remind us that strength and stillness can coexist, that pressure can create peace, that even the most extreme forces in the cosmos can express themselves through quiet, unwavering presence. Their gravity is a whisper that says, I hold, I endure, I remain. One of the most mesmerizing qualities of neutron stars is their spin. When a massive star collapses into a tiny sphere, it doesn't simply shrink, or it conserves its rotational momentum. Like a figure skater pulling their arms inward, the star spins faster as it contracts. A sun that once turned slowly, taking days or weeks to rotate, becomes a neutron star that can make a full rotation in just a few seconds, or even faster. Some spin hundreds of times each second, creating cosmic rhythms too precise to belong to anything so chaotic as a dying star. Imagine drifting near such a star. From afar, the rotation feels serene, almost silent, a gentle turning, like a breath in motion. But as you move closer, the speed becomes astonishing, a city-sized sphere spinning dozens or even hundreds of times each second. Yet the star does not wobble, it does not shake. Extreme gravity locks everything in perfect symmetry. No matter how fast it spins, the neutron star remains calm and centered, like a dancer holding a pose through impossible motion. If you hovered just above the surface, you would be swept around at a significant fraction of the speed of light. Space itself would seem to blur at the edges, drawn along by the star's rotation. The magnetic field lines, vast invisible tendrils stretching into the dark, would twist and coil with the star, carrying charged particles in wide arcs that glow softly in the high-energy light. But despite the unimaginable speeds, there is a profound beauty in the precision of it all. Neutron stars spin with remarkable consistency. Some act like the universe's most reliable metronomes, their rotation so steady that scientists use them as cosmic clocks. Over years, their pulses barely shift, drifting only by microseconds, a level of stability that no machine on Earth could match. Let your breath fall into a rhythm now, slow even, steady, like the soft turning of a distant neutron star. Inhale, exhale. Imagine that each breath echoes the star's rotation, a quiet cycle repeating through the dark, a whisper of movement that persists across millions of years. But even stars that turn like whispers eventually slow down. Tiny amounts of energy leak away as radiation. Particles escape along the magnetic poles. The spin, once fierce, gradually calms. What begins as a furious rotation becomes, over time, a gentle twirl. These stars are born in chaos but age into serenity, a reminder that even the fastest motions eventually find rest. There's a tenderness in that slowing. A life that begins with a violent collapse and a breathtaking spin eventually settles into long, quiet rotations. A journey from intensity to tranquility, from fire to stillness. Think of the moments in your own life when things whirl too fast. Responsibilities, emotions, thoughts spinning like storms. And notice how, with time, the rotation slows. How balance returns, how even the fastest spin eventually finds its centre. Neutron stars embody this truth. Their rotations, extreme yet precise, are the universe's way of showing that motion can be calm, that speed can still be serenity, that even a star turning hundreds of times every second can feel, from a distance, like a soft whisper in the dark. If the gravity of a neutron star is its anchor, then its magnetic field is its wild and unseen weather, a vast invisible storm swirling around the star with a strength beyond anything the human mind naturally grasps. Even an ordinary neutron star carries a magnetic field trillions of times stronger than Earth's, and in the most extreme cases, in the exotic class we call magnetaires, these fields become so intense they can twist atoms, shatter molecules, and reshape particles at distances far beyond the star's surface. Yet for all their ferocity, these magnetic fields move with the grace of something ancient and disciplined, like a slow current beneath deep, still waters. Imagine drifting toward a neutron star suspended in quiet space. You would see no obvious signs of turbulence, no storms of the kind we know on Earth. But as you approached, you would sense a presence, a tension in the vacuum, a subtle pulling on the tiniest threads of your being. The magnetic field extends far beyond the star, a vast cocoon of influence shaping particles, guiding radiation and sculpting the space around it. These magnetic fields are born in the collapse. When the core of the star shrinks from the size of a sun to the size of a city, its magnetic field concentrates, intensifying like ink pressed into a smaller and smaller circle. Lines of magnetic force that once spanned millions of kilometers are squeezed inward, twisting tighter, growing stronger, forming loops and arcs that stretch far into the void. If you could see these fields, truly see them, they would resemble luminous ribbons wrapping the star in delicate geometry. Each line a path along which charged particles race, spiraling, accelerating, and emitting light in high-energy wavelengths. These beams of radiation can sweep across space like cosmic searchlights. Sometimes, when aligned just right, they flash past Earth in perfect pulses, the signature of a spinning neutron star greeting us across thousands of light years. Take a slow breath now, imagining these invisible currents drifting around you like fine strands of silk. There is no chaos here, despite the immense power. The magnetic field is stable, structured, intentional. It is the star's silent architecture, shaping each moment of its existence. In the most extreme neutron stars, the magnetars, this architecture becomes a cathedral of force. Their magnetic fields are the strongest known in the universe, capable of deforming the crust, cracking the surface, and releasing bursts of energy so intense they can momentarily outshine entire galaxies. Yet even these eruptions feel less like explosions and more like deep shifts, a tectonic sigh in a star made of pure neutron matter. But outside these rare disruptions, the magnetic field simply is strong, steady, quiet. A presence felt more than seen, like the emotional weight of a memory that hasn't faded. As you relax deeper into your pillow, imagine the soft glow of charged particles tracing loops around the star, spiraling gently, drawn by invisible hands. Let the magnetic field become a metaphor, a reminder that some forces in life are unseen, and yet they guide us, shape us, hold us in quiet patterns. Not all storms roar. Some hum with a calm that only becomes visible when something small passes through them. Neutron stars teach us that even the invisible can be powerful. That strength does not require noise, and that the quiet architecture of forces unseen can shape entire worlds. Not all neutron stars shine in the same way. Some, by a gentle alignment of rotation and magnetism, become pulsars, the universe's most precise beacons. Their magnetic poles, where charged particles stream outward in narrow jets of radiation, sweep across the cosmos like the beam of a lighthouse turning through fog. And each time that beam crosses Earth's line of sight, we see a pulse, steady, rhythmic, unwavering, like the heartbeat of a star that has survived its own death. Imagine drifting in open space far beyond any planetary warmth, where the darkness feels endless and still. Everything is quiet, everything is vast. Then, in the distance, a faint flicker appears, a soft flash repeating over and over with perfect timing. Not hurried, not frantic, just steady, measured, ancient. You focus on the light, letting it guide your attention like a lantern carried by a traveller walking slowly across the night. That repeating flash is not the star brightening and dimming. It is the beam rotating past you, sweeping through the darkness as the neutron star spins. Some pulsars rotate once every second. Others, the millisecond pulsars, rotate hundreds of times in the same span. Yet despite their incredible speed, the pulses remain so precise that astronomers compare them to atomic clocks. They barely drift, they barely waver. Even after millions of years, the timing remains astonishingly stable. Breathe slowly now, imagining each pulse as a soft inhale and exhale. The rhythm is comforting, predictable, a reminder that even in a universe filled with change, there are steady signals guiding us through the dark. Pulsars embody that steadiness, a kind of cosmic reliability that transcends distance and time. If you could hover nearby, you would watch arcs of radiation spiraling outward from the magnetic poles, invisible light in wavelengths the human eye cannot see. These beams are shaped by the magnetic field, funneled along lines that twist outward like threads of pure energy. Their sweep through space creates the illusion of blinking, though the star itself never truly blinks. It simply turns, calmly, consistently, eternally. Pulsars teach us about rotation, about magnetism, about the structure of neutron stars, but they also teach us something quieter, something more human. They show us the comfort of repetition, the peace in patterns, the way a steady rhythm can anchor the mind, slow the breath, and bring rest even in vastness. Their pulses arrive like gentle reminders that time, no matter how strange or stretched, moves forward in soft, even intervals. Some pulses slow down gradually, losing just a fraction of a millisecond per century. That change, though tiny, tells astronomers about the star's interior, its superfluid layers, its crust, its magnetic strength. Each pulse carries a piece of the star's story, whispered across the vacuum with the patience of something that has existed longer than human history itself. As you settle deeper under your blankets, imagine the sky filled with these slow, whispering signals. Hundreds of tiny lighthouses, each one turning, each one sending out its quiet pattern. You may never see them with your eyes, but their presence threads through the galaxy like a soft cosmic heartbeat. Pulsars are reminders that even in darkness there are rhythms to follow, signals to listen for, patterns that guide us gently forward. Not every neutron star calls out across the cosmos. Some remain silent, or at least silent to us. They emit no steady radio pulses, no rhythmic beams that sweep like cosmic lighthouses. Instead, they drift through space in near invisibility, faint embers of collapsed giants, their voices low, their presence subtle. These are the quiet neutron stars, the ones that reveal themselves only through the softest signatures, a whisper of heat, a trace of X-rays, a faint gravitational tug. They are the stars that hide in plain sight, known not for their signals, but for their silence. Imagine floating through the vastness of space and passing by one of these quiet remnants. You would see very little at first, maybe a dim glow, barely brighter than the background of the universe. No beams, no pulses, just a small dense sphere hanging in the dark, almost reluctant to be noticed. It doesn't announce itself, it simply exists, calm and steady, like a drifting ember left after a long-forgotten fire. These neutron stars do not lack energy or structure. They possess the same immense density, the same gravity that bends light, the same crystalline crust, the same superfluid core. They are as extraordinary as any pulsar or magnetar, but their magnetic fields may not align in a way that sends beams toward us. Or their rotation may have slowed, or their radio emissions may be too faint, absorbed by dust, or riskily pointed in directions where Earth will never be. Their silence is not absence, it is geometry, orientation, chance. Take a slow breath, letting air settle deep into your lungs. Picture one of these quiet neutron stars as a metaphor for the voices in life that do not shout but still carry immense presence. Some things don't need to announce themselves to have impact. Some truths live quietly and still change the world. Some people speak softly and still shape the rooms they enter. The quiet neutron stars are like that. Reminders that silence can hold strength just as powerful as expression. Scientists have discovered these hidden stars through their faint heat signatures. Born blisteringly hot, they cool slowly over millions of years, shedding their thermal glow into the void. That glow, though gentle, can be detected if we look closely enough, and sometimes these stars reveal themselves through gravitational clues, the subtle wobble of a companion star, the tiny distortions of space around them. They do not speak in pulses, they speak in presence. If you were to hover above the surface of one of these silent stars, the quiet would feel deeper than any earthly silence. No wind, no light scattering, no sound, just the soft hum of radiation sliding outward like warmth drifting from a stone left in the sun long after sunset. In that stillness, the star carries the memory of its collapse, the echo of a supernova preserved in dense neutron matter. Let your thoughts sink into that stillness. Imagine the comfort in a presence that doesn't need to shine brightly to exist meaningfully. The universe makes room for loud stars and quiet stars, flashing signals and steady embers. There is no hierarchy, only variety. And among that variety, the quiet neutron stars remind us that some of the most extraordinary things in the universe do their work in silence. They do not call attention to themselves, they simply endure. They persist in their gravity, their density, their calm. Every neutron star has a voice, but some speak so softly that only time, patience, and careful listening can reveal their story. Among all the varieties of neutron stars, there is one class that stands apart, wilder, stranger, more intense than the rest. These are the magnetars, stellar remnants whose magnetic fields are so powerful they stretch the limits of physics itself. If an ordinary neutron star is a quiet ember, a magnetar is a condensed storm. Its magnetic field is the strongest known in the universe. Trillions of times stronger than Earth's, strong enough to twist atoms, fracture its own crust, and reshape the space around it like a sculptor working with invisible clay. And yet, paradoxically, magnetars often appear serene from a distance. Small, dim stars suspended in a gentle glow. Their surface light does not reveal the forces hidden within. It is only when those forces shift, crack, or flare that the star reveals its true nature. Imagine drifting toward a magnetar, floating in soft darkness. At first, nothing seems unusual. Then, slowly, you begin to feel it. A subtle pressure in the vacuum, as if the space around you has thickened. You might see ghost-like arcs of energy tracing the magnetic field lines, each one looping outward before curving back toward the star. These arcs are invisible to the human eye, yet, in your imagination they appear as gentle ribbons, shimmering faintly, holding shape through sheer force. The magnetic field is so strong that, if you were somehow holding a piece of metal from thousands of kilometers away, it would begin to deform in your hand. If you could somehow bring a credit card close, a human symbol of simplicity, the field could erase it effortlessly from half the distance to the moon. But magnetars do not express this power with violence. They carry it quietly, like a dormant storm waiting for the right moment to breathe. Take a slow, steady inhale. Feel the tension rise with the breath, then let go on the exhale, just as a magnetar occasionally releases its pent-up energy. Sometimes the magnetic field becomes too intense for the crust to hold. The star quakes, a sudden fracture in a shell harder than diamond. These starquakes unleash bursts of radiation so powerful they can be detected across the galaxy, even from thousands of light years away. In those moments, a magnetar can outshine an entire galaxy for a fraction of a second. A brief, brilliant flash, a cosmic exhale. But after the flare, the star returns to its quiet state. The glow softens, the fields settle. The storm folds inward once more, waiting, breathing, balancing the tension between unimaginable pressure and perfect calm. That is the magnetar's dual nature. Delicate stillness wrapped around overwhelming force. As you lie peacefully, imagine this balance in your own life. The strength you carry inside, the quiet exterior, the moments when energy builds and the moments when it releases in gentle waves. The universe is full of extremes, yet it always finds ways to hold them together in harmony. Magnetars are the ultimate expression of intensity and restraint. They show us that power does not always roar. Sometimes it hums, sometimes it glows, sometimes it rests patiently in the dark, waiting for the slightest shift. And even though their magnetic storms are beyond comprehension, their presence is a reminder of something deeply human, that our inner forces, our thoughts, our emotions, our memories, can be immense, yet still held in quiet balance. A magnetar is the cosmos's most extreme whisper, soft in appearance, fierce in essence, and endlessly fascinating in the long, slow unfolding of its life. Beneath the soft glow of a neutron star lies one of the strongest structures in the universe, its crust. A thin, rigid shell, only about a kilometer thick, yet harder than diamond, harder than steel, harder than anything we can create or imagine. It is a surface forged under unimaginable pressure, where atoms lock into patterns so tight and so stable that even gravity, fierce as it is here, cannot crush them completely. This crust is the star's armour, its final boundary, the fragile line between the calm vacuum of space and the impossible density beneath. Imagine drifting closer to such a surface. From far away it looks smooth, almost too smooth, like the surface of a pearl suspended in darkness. But as you approach, faint irregularities appear. Tiny ridges, subtle cracks, minute imperfections no more than a millimetre high. On Earth, they would be insignificant, less than the thickness of a fingernail. But on a neutron star, these mountains can be the size of skyscrapers in terms of mass. A bump no taller than a grain of sand could outweigh an entire mountain range. The crust is a paradox. It is rigid, yet constantly under stress. Gravity squeezes inward with unimaginable force. Magnetic fields twist and pull at it. The superfluid interior churns beneath it like a quiet ocean, with no friction. All these forces press against the crust, and yet it holds. Stable, steady, resilient. Take a slow breath. Imagine tension held in perfect balance. The crust is the star's stillness, the shell that does not crumble, even while supporting the weight of a collapsed giant. If you could place your hand on this crust, something no human technology could ever allow, you would feel nothing like rock or metal. You would feel the resistance of matter at its limit. A lattice of nuclei packed closer than any material on Earth, arranged in exotic patterns that form under pressures trillions of times greater than those found in our planet's deepest core. This crust can crack. Sometimes the magnetic field twists enough to deform it. Sometimes stresses build up until the shell can no longer hold. When it snaps, the release is sudden. A starquake. The neutron star's rotation stutters, then speeds up by a tiny amount. A glitch. The crust shifts, rearranging itself in microseconds, sending ripples of energy outward across space. But these cracks do not weaken the star. They are part of its life cycle. Just as Earth reshapes itself with earthquakes, neutron stars reshape themselves with starquakes. Though the forces involved are millions of times greater, yet still expressed in calm and elegant adjustments. Let the idea settle around you. Even the strongest structures yield sometimes. Even the hardest shells must flex, shift, realign. Strength is not the absence of cracks. It is the ability to continue holding shape despite them. As you breathe in, imagine the crust resting under immense gravity. As you breathe out, imagine it holding, steady and unbroken. Every layer of the neutron star depends on this shell, this thin, powerful boundary between the extremes of matter and the silence of space. The crust of a neutron star is a reminder that resilience doesn't always look dramatic. Sometimes it looks like stillness, like a surface that barely moves, barely changes, yet supports a world of pressure beneath. In that stillness, there is a quiet strength, one that endures for millions of years, holding the star together through time, gravity, and transformation. If you could move past the crust of a neutron star descending into its interior, you would enter a realm so strange, so unlike anything on Earth, that language begins to falter. Beneath that hardened shell lies a vast ocean, not of water, not of molten rock, but of pure neutrons flowing together in a state known as superfluidity. It is one of the most extraordinary states of matter known to physics, a liquid without friction, without resistance, without turbulence, capable of moving forever once stirred. Imagine standing at the surface of a quiet lake. Now imagine touching the water and feeling nothing push back. No drag, no resistance, only smooth, silent movement. that gives only the faintest hint of what exists inside a neutron star. In this core, neutrons glide past each other with perfect ease, moving as if gravity's crushing pressure and the density of a collapsed sun simply don't apply. The laws of physics that govern everyday life soften here, giving way to quantum rules that feel more like poetry than mechanics. Take a slow, gentle breath. Let it flow in, then out like a wave that knows exactly where it's going. That flow, easy, quiet, unbroken, mirrors the motion inside a neutron star's core. There is no friction to slow things down, no internal resistance to scatter energy. Once a flow begins, it can persist for millions of years. The core becomes a place where motion can last longer than civilizations, longer than galaxies, longer than entire epochs of cosmic time. If you could drift through this interior as a weightless observer, you would see no currents or churning tides. Everything would appear calm, suspended, unified. Neutrons behave collectively rather than individually, forming a seamless quantum fabric that responds to force as one harmonious whole. Temperature differences, pressure variations, none of these create turbulence. The superfluid simply adjusts, quietly and without struggle. Scientists believe this superfluid core is responsible for many of the neutron star's most mysterious behaviors. Glitches, sudden, tiny jumps in the star's rotation, may happen because the superfluid interior rotates differently than the crust. Like two dancers moving to the same rhythm, but in subtly different steps, the core and crust occasionally slip out of sync. When the tension grows enough, the superfluid transfers some of its rotational energy to the crust, causing the star to suddenly spin a little faster. Even this adjustment, this sudden sharing of energy, happens in a way that reflects deep calm rather than violence. The star realigns itself in microseconds, settling immediately into a new equilibrium. The vast internal ocean, despite its quantum strangeness, behaves with perfect poise. Let your mind wander gently across this image, a liquid at the heart of a dead star, flowing endlessly, silently, effortlessly. There is something soothing in that idea, the notion of motion without interruption, of energy that does not fade, of a steady rhythm that persists through unimaginable pressure and time. And perhaps in a way, this superfluid core mirrors something in us, the parts of ourselves that remain calm even when the surface cracks, the quiet centre that persists beneath the noise of daily life, the deeper flow that continues regardless of pressure. Inside a neutron star, the superfluid core is the star's heart, not in warmth or emotion, but in continuity. It keeps the star balanced, stable, and timeless. A quiet engine running beneath the crust, unceasing, unhurried, undisturbed. In the universe, even the strangest places hold pockets of perfect calm. For all their calm, for all their symmetry and silence, neutron stars occasionally reveal a sudden and surprising quirk. In an instant, faster than a heartbeat, faster than a blink, the star's rotation speeds up, just a tiny bit, a fraction of a percent, but enough for scientists to notice, enough to remind us that even the quietest, most stable objects in the universe are not entirely still. These sudden jumps are called glitches, starquakes, rotational jolts, cosmic adjustments deep within the star's interior. Imagine a perfectly steady rhythm, a ticking clock, a metronome sweeping side to side in flawless timing, and then, without warning, the beat jumps ahead. Not by much, but unmistakably. The rhythm resumes immediately afterward, steady as ever, as if nothing had happened. That is what a neutron star glitch feels like, a momentary skip in an otherwise eternal pulse. Scientists believe these glitches originate in the superfluid core we explored in the last section. Deep inside the star, neutrons swirl in frictionless motion, rotating at a slightly different speed than the rigid crust above them. Over time, the crust slows ever so slightly, losing energy through radiation. But the superfluid interior continues turning at its own pace, unbothered, unresisting. The difference grows, the tension builds. Then suddenly, the core transfers some of its stored rotational energy to the crust. The entire star jolts forward in speed, like a dancer catching up to the music with one sharp, precise step. In that instant, the star realigns itself, core and crust coming back into harmony, the difference between them erased. Take a slow inhale and imagine that gentle shift, the subtle release of tension, the quiet readjustment of something under pressure. Exhale and let the thoughts settle. Even the smallest changes can carry deep meaning when happening on such enormous scales. Another possible source of glitches lies in the crust itself. The hardest material in the universe is not immune to stress. The crust bears the weight of a collapsed moon-sized object pressed into city-sized dimensions. It is constantly pulled by magnetic fields, constantly influenced by the flow of the core beneath. Eventually, the crust cracks, a starquake, and when it does, the surface rearranges abruptly, shifting the star's moment of inertia and causing it to spin just a bit faster. But again, there is no chaos in this adjustment. The neutron star does not shatter, does not tremble visibly, it simply resumes. The new rotation becomes the star's steady pace, as calm and measured as ever. The glitch is momentary, yet perfectly natural in the life of a neutron star. Let your mind drift for a moment to times when you have felt out of sync, when internal and external rhythms did not match. Moments when you paused, readjusted, and moved forward with new alignment. A neutron star glitch is not a rupture, it is a correction, a return to balance, a small, precise shift that restores harmony within. From Earth, these glitches arrive as slight changes in the timing of pulses. A pulse arrives earlier than expected by just enough to notice. Scientists record the change, study it, unravel its meaning. And in those tiny shifts, we glimpse the living dynamics of something unimaginably dense and ancient. A neutron star's life may seem still, but deep inside, quiet tensions rise and fall. And every so often the star reminds us, with a tiny jolt, that even the most stable objects in the universe adjust, adapt, and realign themselves. Not all neutron stars wander alone through the cosmic night. Many live their long, quiet afterlives with a partner, a companion star orbiting so closely that the two objects become inseparable, locked in a gravitational embrace that can last billions of years. These binary systems are some of the most breathtaking choreographies in the universe. Two stars circling one another in a silent, endless dance, their motions guided by gravity's invisible hand. Imagine drifting through deep space and encountering such a pair. At first, you might notice one faint point of light, pulsing gently. Then, beside it, another glow. Softer, perhaps warmer, perhaps older. As you move closer, their motions reveal themselves. The two stars circle each other with slow, deliberate grace. No rush, no collision. Just a steady orbit, like two lanterns carried by dancers who never tire. The neutron star, small and impossibly dense, curves the fabric of space with its gravity. Its companion, often a normal star, sometimes a white dwarf, or even another neutron star, responds to that curvature, moving in a perfect path defined by physics so elegant it feels like choreography. Their orbit may take hours, days, or years to complete a cycle. But whichever the pace, the rhythm is constant, reliable, and deeply calming. Take a slow breath in and imagine the pull between them, a gentle force, steady and consistent, linking two distant objects into one system. Exhale, and imagine yourself floating between them, surrounded by the quiet hum of their shared gravity. In some systems, the neutron star's magnetic field interacts with its companion. gas drifts from the larger star toward the smaller one, spiralling inward and forming an accretion disk, a glowing ring of hot matter orbiting closer and closer to the neutron star's surface. This glow can shine in X-rays, soft and ethereal, visible across great distances. But even this transfer of matter, intense as it is, carries an unexpected calm. The inward flow is smooth, gradual, almost like a river drawn toward a deep well. And in the rarest and most awe-inspiring cases, two neutron stars orbit together. Two city-sized spheres of super-dense matter circling in a cosmic spiral, their movement slowing over millions of years as they radiate gravitational waves, ripples in space-time itself. Each orbit tightens, the dance drawing the stars ever closer in a slow, silent embrace. It is one of the universe's most intimate motions, witnessed only through the faint trembling of space-time detected on Earth. As you breathe, let the image settle, two stars, tiny but powerful, moving around each other in perfect balance. A reminder that connection can be quiet, steady, enduring, not dramatic or loud, but persistent through time. Binary neutron star systems tell us something about companionship, that even in the coldest stretches of space, gravity binds objects into relationships that last longer than any life on Earth. These systems are stories of mutual influence, shared motion, and the long arc of cosmic patience. Sometimes the orbit remains stable forever. Sometimes the stars eventually merge in a brilliant explosion, creating heavy elements and sending waves through space-time. But long before that final moment, the dance itself is what defines them. The slow, spiraling rhythm of two bodies held together by an invisible force. Think of the relationships in your own life, the gentle pulls, the steady orbits, the quiet exchanges of energy over time. The universe mirrors these patterns in ways both grand and subtle. Two stars, one shared path, a dance written into gravity itself. When two neutron stars orbit each other, their dance is not confined to the space between them. Every motion, every turn, every tightening spiral sends out faint disturbances into the fabric of space-time itself. These disturbances are gravitational waves, ripples that travel across the universe at the speed of light, stretching and compressing the very structure of reality as they pass. They are whispers in the dark, soft tremors that carry the story of distant stars to any world quiet enough to listen. Imagine space-time as a vast, calm ocean. Most of the time it lies still, unbroken. But when massive objects move, especially objects as dense and compact as neutron stars, they stir the water. Gentle waves radiate outward, travelling billions of kilometres without losing their shape. These waves don't shake like sound. They don't glow like light. Instead, they gently stretch and squeeze everything they touch, altering distance itself by amounts far smaller than the width of a proton. Subtle, delicate, nearly imperceptible, yet even these subtle ripples reveal incredible stories. Take a slow breath in and picture the fabric of reality inhaling with you, a gentle widening. Breathe out and imagine it contracting, a soft compression. This is how gravitational waves move, not through displacement, but through the rhythm of space expanding and contracting as the waves pass through. When two neutron stars orbit each other, the waves they release grow stronger as they spiral closer. The dance tightens, the rhythm quickens, the stars draw nearer, losing energy to the waves that ripple outward. It's a slow and poetic surrender. Millions of years spent gliding in a spiral that becomes ever more intimate, until the two stars finally meet in a brilliant, world-shaping collision. But long before that final moment, their waves arrive here on Earth. In 2017, for the first time in human history, we detected such a signal. Instruments deep underground, so sensitive they can measure shifts smaller than a single atom, registered a faint, fleeting quiver. the echo of two neutron stars merging 130 million light-years away. The signal lasted less than 2 minutes, but in that brief moment the universe told us a story that had been travelling toward us since before humanity existed. Let yourself feel the quiet immensity of that idea. Two stars in a distant galaxy moving in their final spiral, their waves spreading outward through the cosmic night, crossing clusters, voids and lightless expanses, until one of those waves touched Earth, so gently that only the most careful instruments could feel it. Even so, the ripple carried truth. It told us the masses of the stars, their distance, their spiral speed, their collision. It whispered that the universe is interconnected, that motion in one corner influences space in all others. Breathe slowly, imagining a ripple moving outward from a distant point, passing under you like a soft vibration in a quiet room. Not disruptive, not alarming, just a reminder that the cosmos is alive with subtle movement. Gravitational waves are proof that the universe is not static. They show us that space is flexible, fluid, capable of carrying messages from places we will never reach. They reveal that every change, and even the most distant, leaves a trace. And neutron stars, with their immense density and slow spiraling dances, are among the most powerful creators of these cosmic ripples. They stir the deep ocean of space-time, gently, patiently, until their final embrace sends one great wave across the cosmos. Not all light from neutron stars comes from their own surfaces. Sometimes, a neutron star shines because something else is falling toward it, drifting inward in a slow, spiraling descent. When a neutron star has a companion, gas can stream from the other star, pulled gently but irresistibly by gravity. This gas forms a bright swirling ring around the neutron star called an accretion disk, and as the gas spirals closer and closer, it heats up until it glows in soft, powerful X-rays, a beacon shining from the threshold of the densest object in existence. Imagine drifting near such a system. Two stars orbiting one another, one dense and silent, the other shedding wisps of its outer layers. Those wisps fall inward in long, graceful arcs, like silk ribbons caught in a slow whirlpool. As the gas circles the neutron star, friction and gravity heat it to millions of degrees. The hotter it becomes, the brighter it glows. Not in visible light, but in invisible X-ray waves that travel straight through the darkness, reaching us across vast distances. Take a slow breath in, imagining those glowing ribbons spiraling inward. Let your exhale follow their descent, soft and steady, drifting deeper toward the star below. As the gas approaches the surface, it accelerates, moving faster than any wind or river on Earth. The final moments before it strikes the surface of the neutron star are among the most energetic processes in the universe. But from afar, all you would see is a faint, steady glow, a halo of X-ray light radiating outward, soft as a distant sunrise. In these systems, the neutron star behaves like a quiet island in a bright storm. The accretion disk rotates around it like a luminous ring, with material constantly circling, waiting for its final fall. The magnetic field of the neutron star may guide this infalling matter toward the magnetic poles, creating hotspots on the surface that shine like tiny, radiant lanterns. As the star rotates, these hotspots sweep across space, creating pulsating X-ray signals, quieter cousins of the radio pulses emitted by classic pulsars. There is a serene beauty in this process, despite the energy involved. Everything moves in spirals, in curves, in smooth arcs shaped by gravity's patient hand. The accretion disk is not chaotic, it is orderly, a soft, glowing whirlpool feeding a star that has outlived its own fire. These X-rays help scientists understand neutron stars in remarkable detail. By watching how the light flickers, how it brightens, how it fades, we learn about the star's surface, its spin, its magnetic field, even the texture of its crust. The light becomes a language, a way for the neutron star to communicate without words, without pulses, simply through the glow of falling matter. Let yourself imagine this glow now, a faint shimmering ring of light surrounding a city-sized star suspended in a sea of darkness. The gas spiralling inward like a long, slow breath being drawn into the chest of the cosmos. Each particle, once part of a living star, becoming part of something new. And just as neutron stars teach us about strength and stillness, accretion teaches us about transformation, about how things fall, merge, and change, about how motion becomes light, about how even collapse can produce beauty. In the silent night of the universe, these X-ray beacons shine softly, reminders that even in the deepest shadows, there are places where matter glows with the heat of becoming something new. Some neutron stars spin quickly when they are born, but others, the fastest ones of all, achieve their breathtaking rotation through a long, intimate partnership. These are the millisecond pulsars, stars that whirl hundreds of times per second, spun up over millions of years by the slow, steady gift of angular momentum from a companion star. They are not born fast, they become fast, shaped by time, gravity, and the quiet exchange of matter between two aging suns. Imagine a neutron star that once spun slowly, its pulses arriving like calm, measured breaths separated by seconds. It drifts through its orbit beside a companion, perhaps a dying red giant or a small white dwarf. At some point in its partner's late life, material begins to drift away, tugged by the neutron star's gravity. Gas flows from the companion like a soft, continuous stream, spiraling toward the neutron star in a luminous arc. Take a slow breath and imagine this stream as a ribbon of stardust pulled gently toward a waiting hand. As the gas settles into an accretion disk around the neutron star, it transfers not just mass but motion. The inward spinning material nudges the neutron star faster and faster and faster still. Over thousands or millions of years, the neutron star's rotation accelerates until it becomes one of the fastest spinning objects in the universe. Some complete more than 700 rotations in a single second, a pace so extreme that the crust strains against the centrifugal force, held together only by gravity's unwavering grip. Yet from a distance it feels serene, even graceful. A millisecond pulsar does not feel frantic or chaotic. Instead, its pulses arrive like delicate vibrations, quick, precise, almost musical in their regularity. Each rotation produces a beam of radiation that sweeps across the cosmos, creating flashes so rhythmic that they rival the best timekeeping devices humanity has ever built. Scientists study millisecond pulses like clocks woven from collapsed stars. Their pulses barely drift. Their timing is almost perfect. Some are so stable that astronomers propose using them as a galactic navigation system, a cosmic GPS written into the turning of ancient suns. Let your breath grow soft, and even as you imagine this, a star spinning so fast it seems impossible, yet doing so with absolute calm. No wobble, no strain, no instability, just a smooth, ceaseless rotation that persists across eons. The relationship between the neutron star and its companion eventually fades. The companion star may shrink, quiet, or drift away. The accretion may stop, but the spin remains, a memory imprinted on the neutron star's very structure. What was once shared motion becomes its own. The star continues to whirl for billions of years, carrying the legacy of its long partnership in every rotation. There is a gentle metaphor in this. Sometimes the most profound changes in our lives happen slowly, through steady exchanges with the people around us. A little energy given here, a little momentum received there. Over time, those exchanges shape who we become. Quietly, gradually, almost imperceptibly. Just as the neutron star grows faster through its companion's gift, we grow through the influences that move through our lives. Millisecond pulsars are reminders that transformation doesn't always happen in an instant. Sometimes it is the culmination of long relationships, slow gradients, shared gravity. And in their quiet, rapid pulses, the universe reveals one of its most beautiful rhythms, a star turning hundreds of times per second, each rotation a whisper of the bond that once shaped it. By now, we've wandered through several forms of neutron stars: pulsars, quiet remnants, magnetars, millisecond speedsters. Each one feels distinct, as if they belong to different categories of celestial beings. But in truth, they're all variations of the same underlying mystery, a collapsed core of a massive star transformed by pressure and gravity into one of the strangest objects the universe can create. Scientists call this collection of forms the neutron star zoo, a gentle name for a spectrum of extremes. Imagine standing at the centre of a quiet observatory, surrounded by screens showing different neutron stars. On one, a pulsar flashes with perfect rhythm. On another, a magnetar glows with unpredictable storms of energy. A third shows a faint ember, a quiet star with no pulses at all. Yet behind their differences, the same story hums, a star that died but didn't disappear. Take a slow breath, letting that unity settle. Exhale into the idea that one origin can lead to many lives. A neutron star's appearance depends on many things: how quickly it spun when it was born, how strong its magnetic field was, whether it gained or lost mass over time, whether it had a companion to share energy with. These differences accumulate like variations in personality, shaping the star's behaviour over millions of years. A magnetar, with its intense magnetic storms, may eventually calm into an ordinary pulsar. A pulsar may slow until its beams no longer sweep over Earth, becoming a quiet neutron star. A slow, spinning star may be spun up again by a companion, reborn as a millisecond pulsar. In this way, neutron stars have life cycles, transitional arcs, transformations guided by environment, chance, and time. They evolve, they age, they change identities. Their stories are not static. If you drifted from one neutron star to another, you would witness extraordinary diversity. One might spin like a whisper, sending pulses at the pace of a calm heartbeat. Another might crackle with magnetic tension, ready to flare at any moment. Another may barely glow, its heat fading as it settles into a long, quiet twilight. Yet beneath every variation lies the same impossible density, the same neutron sea, the same crust forged under pressure beyond measure, the same story of collapse, the same calm at the core, the same small radius hiding immense mass. They are siblings shaped by circumstance, each carrying a different expression of the same cosmic truth. Let your breath match that idea, inhale the sameness, exhale the difference. The neutron star zoo shows us something profound about nature, that even when the ingredients are the same, the outcomes can vary in extraordinary ways. Tiny changes in initial conditions lead to vastly different existences. And just like people, neutron stars are shaped not only by how they begin, but by what surrounds them: companions, environment, interactions over time. In the end, the variety of neutron stars helps scientists test the limits of physics. Their differences reveal clues about magnetic fields, quantum states, nuclear matter, and gravity. They are laboratories scattered across the galaxy, each one offering a slightly different experiment, a slightly different insight. But beyond the science, their diversity offers a softer lesson. Identity is not a fixed point. It is an evolution, a spectrum, a gradual unfolding. Neutron stars may be the strangest remnants in the cosmos, but they are also among the most expressive, showing us all the paths a collapsed star can take. Different faces, same mystery, one origin, many destinies. When a neutron star is born, It emerges from the heart of a supernova, an explosion so fierce that temperatures soar to unimaginable levels. In the first moments of its life, the newborn star is hotter than almost anything else in the universe. Millions of degrees, a surface blazing with trapped heat, glowing in X-rays like a piece of cosmic metal fresh from a celestial forge. But as time passes, that heat begins to fade. Not quickly, not dramatically, but slowly, like a memory softening at the edges, persisting long after the moment has passed. Imagine standing a great distance away from a brand new neutron star, watching it cool. At first, its heat radiates outward in waves, invisible but intense. The star sheds energy rapidly, trying to release what the collapse forced inside. Neutrinos, ghost-like particles that pass through matter effortlessly, stream out by the trillions. In just minutes, the star cools from hundreds of billions of degrees to only a few million. A dramatic fall, yet still hotter than any fusion reactor humanity could ever build. Take a slow breath. Inhale warmth. Exhale into the image of that heat drifting away, softly, patiently. As the neutron star settles into its long afterlife, the cooling becomes more gradual. The surface temperature drops to 1,000,000 degrees, then hundreds of thousands. In the end, empty silence of space with no air to carry heat away. Cooling becomes a dance between the star's interior quantum landscape and the vacuum outside. Heat must travel from the superfluid depth through the rigid crust, then out into the void. Nothing rushes. Nothing stirs. The process unfolds over millions of years. From afar, the glow softens. A neutron star that once shone brightly in X-rays dims to a warm ember, its light faint but persistent. Even after 1,000,000 years, it may still be hundreds of thousands of degrees hot. After 10 million years, perhaps only tens of thousands. And even after that, a gentle warmth remains, the memory of a life that began in fire. Let yourself imagine that fading heat as a kind of cosmic nostalgia, the way certain feelings linger long after the moment has passed, the way warmth can stay in the body even after the fire has gone out. Neutron stars carry their histories within their temperature, cooling slowly, holding their past like a soft, enduring glow. Scientists study this cooling to understand the interior of neutron stars. The rate at which a star loses heat reveals clues about its crust, its superfluid core, its exotic particles. A faster than expected cooling might hint at new physics, particles we haven't yet discovered, interactions we don't fully understand. Even the star's fading warmth becomes a language, a whisper telling us what lies beneath its surface. Picture yourself drifting near one of these ancient remnants. You wouldn't feel heat, not at a safe distance, not in the vacuum of space, but you might sense its presence, the faint glow of something that once burned fiercely. It would feel like standing near a campfire long after it has turned to embers. The flames are gone, but the warmth remains, woven into the air with a quiet intimacy. Now breathe gently, letting the thoughts settle. Even after the brightest events of our lives, something warm lingers, a memory, a lesson, a feeling. Heat fades, but not all at once. Neutron stars teach us that cooling is not decline. It is transformation, a gradual shift from intensity to endurance, a slow release that makes room for calm. The heat of their birth softens into the warmth of existence, a temperature that fades but never fully disappears. Around a neutron star, an object so dense it bends space and warps time, there exists something unexpectedly delicate, an atmosphere. Not like Earth's vast blanket of air, stretching tens of kilometers above oceans and forests. A neutron star's atmosphere is astonishingly thin, a fragile film only a few centimeters thick. Yet within this sliver of gas lies a world of physics so extreme and beautiful that even a breath's worth of material becomes a window into the star's strange nature. Imagine drifting toward the surface of a neutron star. The space around you tightens subtly, gravity deepening with every kilometre you descend. The surface grows, larger in your view, glowing softly with fading heat. Then, just above that rigid crust, just before you reach the neutron-rich matter beneath, you pass through the atmosphere. It is so thin you could glide through it in a single blink. But despite its small size, it is a realm shaped by extremes. The gas here is made mostly of hydrogen and helium, stripped of electrons by the intense heat and magnetic fields. These atoms behave differently than they do anywhere else. Under the crushing gravity, they compress into thin layers, almost like pages of an invisible book pressed tightly together. If you were to place your hand through this atmosphere, ignoring the fact that such a thing is impossible, you would feel nothing like wind. The particles are too sparse, too compressed. There is no breeze, no swirls, no weather. Take a slow breath in, letting that stillness settle. Exhale into the idea of a fragile atmosphere held in place by gravity so intense that even a whisper of gas becomes part of the star's identity. Because the atmosphere is so thin, light behaves oddly here. Photons escaping from the star's surface pass through the gas at unusual angles, bent by gravity and distorted by the star's magnetic field. Colours shift, spectra stretch. The thin atmosphere acts less like a sky and more like a shimmering lens, a filter through which the hidden layers of the star reveal themselves. Scientists study the X-rays passing through this atmosphere to learn about the star's temperature, magnetic field, and composition. The way the light changes tells us how atoms behave when pressed tightly enough to collapse the distinction between particles. Even though the atmosphere is only a few centimetres thick, it carries the signatures of the star's deeper secrets. Imagine this atmospheric film as a veil, soft, transparent, and infinitely thin, resting gently over a body of incredible density. It is the final boundary between the neutron star's interior and the vast, cold vacuum of space, a fragile interface where the extreme meets the empty. There's something peaceful in that contrast, a reminder that even the strongest structures can wear delicate coverings. Even the most intense forces can be touched by a brush of softness. Take another breath, slow and steady. Picture the thin atmospheric glow following each exhale, like a film of light spread gently across your thoughts. If you could watch a neutron star from nearby, the atmosphere might flicker subtly as magnetic fields shift across the surface. Tiny hotspots, small as cities but massive beyond comprehension, would glow a little brighter. The surface might appear to shimmer, not because of movement, but because of the way photons struggle through the layers of gas. It is quiet, impossibly quiet, a place where gravity compresses even air into a thin, unmoving sheet. Neutron stars remind us that boundaries can be thin but meaningful, that the edge between intensity and emptiness can be delicate, that even at the threshold of extremes there is space for softness. Deep inside a neutron star, past the crust and the superfluid ocean of neutrons, lies a region where the familiar rules of physics begin to loosen, tilt, and transform. The pressures here are so immense that matter may rearrange itself into unfamiliar forms, particles dissolving, quarks roaming freely, structures shifting into states that scientists can only describe with theories and dreams. This realm is often called exotic matter, not because it is strange for the sake of strangeness, but because it exists beyond the boundaries of what we can recreate on Earth. It is matter pushed to its absolute limits. Imagine travelling downward through the layers of a neutron star. The crust hardens, the superfluid core flows in perfect silence, and then, deeper still, you approach a threshold. A point where density becomes so extreme that neutrons may break apart. Their constituent quarks, normally locked tightly together, might drift freely, creating a soup of fundamental particles without structure. A place where up quarks, down quarks, and perhaps even strange quarks mingle in a quantum sea. Take a slow breath. Let it sink into your chest like a quiet descent. Exhale into the idea of matter unbound, liberated from its familiar constraints. If quark matter exists inside neutron stars, it would be unlike anything we've ever touched or seen. A fluid of pure essence, where particles that usually form protons and neutrons instead flow freely, like colours dissolving into one another on a wet canvas. Some theories suggest that this exotic fluid could be the most stable form of matter in the universe, so stable that a drop of it might convert anything it touches into more of itself. Thankfully, such states exist only under pressures so intense that no laboratory can approach them. In this deep interior, everything is squeezed so tightly that the boundaries between particles blur. New structures may arise: hyperons, which contain strange quarks, condensates of paired particles, phases of matter that behave like both solid and fluid at once. Scientists propose diagrams and equations to describe these states, but the truth remains hidden beneath kilometers of neutron-rich material, a mystery preserved by gravity. And yet, this hidden heart influences the entire star. The way exotic matter behaves can affect how the star cools, how it spins, how it glitches. Even the gravitational waves produced when neutron stars merge carry the fingerprints of their inner composition. The universe whispers clues encoded in ripples, waiting for us to decode them. Imagine that for a moment. Two neutron stars spiraling together, their cores brushing against the limits of physics. When they collide, the exotic matter at their centers is briefly exposed, a flash of the universe's deepest secrets. We cannot see it directly, but its effects ripple across space-time, reaching our detectors as faint vibrations. Take another slow breath. Inhale the mystery. Exhale the wonder. There is something profoundly calming about knowing that the universe holds states of matter we cannot fully imagine. That beneath the crust of a collapsed star lies a place where structure breaks down and rebuilds itself in new forms. A reminder that nature is more inventive, more curious, more patient than we are. And perhaps this exotic matter mirrors something within us. The parts of ourselves that only emerge under pressure, the hidden potentials revealed in the deepest layers of experience. The idea that beneath our outer crusts and quiet surfaces, something more fundamental waits, shaped by forces we can barely name. Neutron stars hold these secrets in silence. They do not reveal them easily. They simply exist, carrying exotic matter at their cores like a treasure locked away, a mystery preserved by gravity, waiting for future generations to understand. Even when a neutron star is cooled, even when its pulses fade and its magnetic storms fall quiet, it still emits a gentle glow. Not a blaze like the sun, nor the brilliant flash of a supernova, but a soft, persistent radiation. A whisper of photons drifting outward from the star's surface. This glow is the lingering warmth of a collapsed giant, the faint afterlight of a life that once burned brighter than imagination. Imagine drifting through the darkness of space, surrounded by silence so complete it feels like a blanket. Then, in the distance, you see a dim, steady shimmer, not bright, not sharp, but unmistakable. A city-sized sphere, glowing with the soft heat of millions of trapped particles slowly escaping into the void. The light is gentle, almost shy, but it carries the essence of the star's history. Take a slow breath in. Imagine that soft glow brightening just a little. Exhale and picture it fading into calm again. The radiation coming from a neutron star is mostly thermal, heat trying to escape from the dense, hot interior through the thin atmospheric film. Because the star is so compact, the light is heavily bent by gravity. Photons that would normally shoot straight up curve around the star making the entire surface visible from almost any angle. It's as if the star draws its own light back toward itself before finally letting it go. This bending creates a unique, serene effect. The star seems to shimmer evenly, with no harsh shadows, no sharp edges, a soft sphere of light glowing through the dark like a lantern placed under thin cloth. Over time, the glow changes. A young neutron star shines primarily in X-rays, its surface so hot that photons burst forth with high energy. As it cools over millions of years, the emission shifts to extreme ultraviolet, then to visible light too faint for all but the most sensitive telescopes. Eventually, after tens or hundreds of millions of years, the star may cool to the point where only infrared photons remain, low energy warmth drifting from its surface like the lingering heat of a stone at dusk. And yet, even this faint glow tells a story. By studying how the radiation changes over time, scientists can learn how heat moves through the crust, how the superfluid core cools, how exotic particles behave deep inside. Every photon is a clue. Every glow is a memory. Think of the ways your own experiences radiate outward, how moments that once burned brightly soften with time, becoming warm recollections, gentle reminders. A neutron star holds its past in precisely this way. Its radiation glow is not a blaze of youth, but the tender afterheat of endurance. As you imagine this glow, let it settle across your thoughts like candlelight spreading through a quiet room. No urgency, no intensity, just the steady, patient release of warmth. If you could hover close enough, protected by impossible technology, you might see tiny hotspots on the surface where magnetic fields funnel heat upward. You might see speckles of brightness where the crust is slightly warmer, where glitches have released bursts of energy. These patterns are like freckles on the face of the star, each one a clue about events long past. The radiation glow of a neutron star is subtle, but it is never meaningless. It is a reminder that even things born in fire eventually find ways to cool, to soften, to emit calm rather than chaos. In the dark of space, this glow is a promise that even the most intense moments can become gentle, and the hottest fires can leave behind a warmth that lasts. For most of cosmic history, neutron stars drifted unseen. Tiny, dense relics hidden in the immensity of space, their light too faint for human eyes, their signals too subtle for ancient telescopes. Only in the last century have we begun to notice them, to tune our instruments finely enough to hear their quiet rhythms. Detecting a neutron star is not like spotting a bright planet or a glowing nebula. It is more like listening for a heartbeat through walls, searching for the faintest vibration from something impossibly distant. Imagine standing in a silent forest at night. At first, all you hear is stillness. But then, as your attention sharpens, subtle sounds emerge. The soft crack of a twig, the whisper of leaves, the faint rustle of wings. Detecting neutron stars is much like that. The universe seems quiet, but once we build tools sensitive enough, we discover that space hums with tiny signals, pulses, X-ray flares, gravitational ripples, thermal glows. Take a slow breath in, feeling your attention expand. Exhale, letting that awareness soften into openness. That is the mindset astronomers use when searching for neutron stars. Patience, calm listening, and trust in the faintest clues. The first neutron stars were detected as pulsars, rhythmic radio flashes sweeping across Earth, like beams from a cosmic lighthouse. Large radio telescopes with their dish-shaped ears picked up signals repeating with uncanny precision. Scientists initially wondered if they were artificial, nicknaming the first detection LGM-1, Little Green Men 1. Only later did they realize the true source, a spinning neutron star calling out across interstellar space with each rotation. Radio waves are still one of our best guides. Pulsars send them out in predictable patterns, allowing astronomers to map their positions, measure their spin, and track their slowing over time. But not all neutron stars speak in radio frequencies. Some reveal themselves in X-rays, bright hotspots on their surfaces flickering with each rotation, or glowing accretion disks feeding them energy from companion stars. X-ray telescopes in orbit around Earth scan the sky for these faint beams, detecting photons that never make it through our atmosphere. Others appear only as warm infrared points, old cooling remnants whose light is barely strong enough to escape the star's gravitational grasp. Sensitive infrared telescopes can pick out these dim embers, revealing neutron stars that no other instrument can see. And then there are gravitational waves. Listening to these requires detectors so delicate they can sense distortions far smaller than an atomic nucleus. When two neutron stars spiral together and merge, the shock wave of their collision ripples across space-time. Instruments like LIGO and Virgo stretch and contract ever so slightly as the wave passes through, recording a signature unlike anything else. Imagine that for a moment. Two stars merging millions of light years away, their final embrace sending a whisper through the universe that eventually touches Earth. A faint vibration carrying the story of a cosmic event long past. Every method, radio, X-ray, gamma ray, infrared, gravitational waves, is a different sense, a different way of perceiving. Together they help us build a full picture of these hidden stars. And through these tiny signals, neutron stars speak to us. Not in words, but in rhythms, glows, and ripples, in patterns that require patience to interpret, in data that resembles music more than brightness. As you breathe, imagine tuning yourself to these signals, listening for the faintest beat, the quietest shimmer of light, the softest ripple in the fabric of night. Detecting neutron stars teaches us that truth doesn't always arrive loudly. Sometimes it comes as a whisper across the cosmos, waiting for someone calm enough to hear it. Long before neutron stars became familiar players in our cosmic imagination, they arrived as mysteries, strange, repeating signals that seemed to come from nowhere. In the late 1960s, astronomers using radio telescopes began recording a pattern that defied every expectation, perfectly timed pulses arriving again and again with the precision of a heartbeat. These signals came from blank regions of the sky, places where no stars appeared in visible light. They were rhythmic, consistent, and unnervingly regular. Imagine sitting beside one of those early radio receivers, the cold metal dish pointed toward a silent patch of night. The equipment hums softly, static crackles, and then a blip, followed by another, then another, tiny flashes of radio energy, spaced so evenly they feel intentional, almost mechanical, almost alive. Take a slow breath, as if you're leaning closer to listen. Exhale softly, letting the mystery drift in like a quiet breeze. The astronomers who first detected these signals did not know what to make of them. Nothing in the sky behaved like this. No star flickered so uniformly. No planet emitted pulses so precisely. And so, with a mixture of curiosity and humour, they labelled the first source LGM-1, Little Green Men 1, a playful nod to the possibility that the signal could be artificial. Of course, it wasn't. But in those early days, the universe had not yet revealed the existence of neutron stars in a form anyone could measure. These pulses were the first hints, the first whispers, of a kind of object no one had imagined in detail. As scientists studied the signals more closely, patterns emerged. The pulse rates matched what might happen if a small, dense object was spinning rapidly, sweeping a beam of radiation across space with each rotation. This idea shifted the narrative. The signals were not artificial. They were mechanical only in the sense that the universe itself moves with intricate precision. breathe gently, letting the thoughts settle, nature has its own rhythms, its own clocks, its own ways of repeating patterns. It soon became clear that these were not lone curiosities. More pulsing sources were found, different speeds, different intensities, all sharing the same essential signature, steady radio bursts timed with astonishing accuracy. The realization dawned slowly but beautifully. These were neutron stars, spinning like cosmic lighthouses, revealing themselves for the first time. Once the mystery unraveled, the discovery reshaped astrophysics. Neutron stars, once theoretical, became real. Their existence confirmed the predictions of decades-old models about stellar collapse and nuclear matter. Each new pulsar found was like a new tone in a cosmic symphony, a rhythm that gave clues about density, gravity, magnetic fields, and the innermost nature of dying stars. Imagine the wonder of that moment. A whole category of star invisible in ordinary light suddenly speaking through radio waves. A hidden world revealed not through brightness, but through rhythm. Today, thousands of pulsars have been discovered, but the memory of those first signals remains iconic. The moment the universe tapped on our instruments and said, "Listen," it is a reminder that some discoveries begin with surprise, with confusion, with signals that seem to come from nowhere, and that listening, patient, curious listening, is often the first step toward understanding. As you breathe in, imagine those early pulses travelling across space, steady, faithful, unchanged for millions of years. As you breathe out, imagine them finally reaching Earth, captured by a metal dish and a scientist awake in a quiet lab at night. From silence came rhythm, from rhythm came recognition, and from recognition came one of astronomy's most beautiful revelations. When two neutron stars meet in their final spiral, after millions, sometimes billions of years circling each other in a tightening dance, something extraordinary happens. In the instant of their collision, matter that has been compressed beyond imagination is violently released. The star cores, once held together by gravity and nuclear forces stronger than anything else in nature, are torn open, and for a brief moment, the universe becomes a forge, hotter and denser than any star, any explosion, any human-made furnace. In that fleeting crucible, heavy elements are born: gold, platinum, uranium, rare earth metals, and countless other atoms too heavy to form in ordinary stars. Take a slow breath in and imagine those elements as tiny embers scattered into the dark. Exhale and picture them drifting outward, carried by shockwaves through the night. For decades, scientists wondered where the universe made its heaviest ingredients. The cores of normal stars cannot produce elements heavier than iron. The process becomes too energetically expensive. Something else had to be responsible for the gold in your jewellery, the iodine in your body, the platinum in electronics, the rare elements in planets. The answer was hidden in the hearts of neutron stars. When they collide, the crushed neutron-rich matter decompresses in a flash. Neutrons bind to atomic nuclei faster than the nuclei can decay, building heavier and heavier elements in a rapid sequence known as the R process. It is nature working at its fastest, stacking neutrons like building blocks, assembling atoms that would otherwise be impossible. Imagine that for a moment. The gold in a wedding ring, the atoms in ancient coins, the precious metals inside satellites orbiting Earth. All of them were created in a moment of unimaginable pressure and heat, born from the collision of stars that had once spun quietly in the dark. As you breathe, let that idea settle around you like warm dust. We carry the relics of neutron star mergers in our hands, our bodies, our world. The explosion that follows such a merger is called a kilonova, a burst of light so luminous it can outshine an entire galaxy for a short time. The ejecta expand into space, cooling, condensing, forming dust grains infused with heavy elements. These grains drift through the galaxy for millions of years, mixing into clouds of gas. Eventually, some of those clouds collapse into new stars, new planets, new worlds waiting to form life. Your body contains traces of these elements. Every living being does. In a poetic way, neutron stars are part of our ancestry, distant relatives in the cosmic timeline, contributors to the ingredients that allow life to exist. Let your breath flow in and out as you imagine that lineage. We are connected to the universe not just metaphorically, but physically, in essence, in dust, in atoms. Even isolated neutron stars play a role. Their magnetic fields shape cosmic radiation. Their gravitational influence stabilizes star systems. Their cooling surfaces help scientists test the boundaries of physics, refining the models that explain how matter behaves under extreme stress. But their greatest contribution is elemental. They are the keepers of the universe's heaviest materials, holding them tightly for ages until, under rare and beautiful circumstances, they release them into the cosmos. Every piece of gold on Earth was created in a moment of pure cosmic violence, and then carried outward by a slow, drifting breeze of stardust. Neutron stars may be small, quiet, and hidden in the night, but their influence stretches across galaxies. They shape the composition of planets. They write their legacy into the chemistry of every world that ever forms. The heaviest parts of us come from the heaviest stars, from their collapse, from their union, from their brilliant endings. Some of the most precise clocks in the universe are not built by human hands. They are born from collapse, from the crushed remnants of ancient stars. Pulsars, especially millisecond pulsars, keep time with a stability that rivals the finest atomic clocks on Earth. Their rotations are so steady, so faithful, that years can pass without a single measurable deviation. In their quiet pulse, the universe offers us a rhythm more precise than anything we could ever engineer. Imagine drifting in space beside one of these stars. With each rotation, a beam of radiation sweeps past, brushing the darkness with an exquisite regularity. Every flicker is like the soft tick of a cosmic clock, marking time not in seconds but in the turning of a collapsed giant. If you close your eyes, you can almost hear it, a steady, gentle beat, patient and unchanging. Take a slow breath in, letting your own heartbeat align with that rhythm. Exhale, and imagine the star continuing its endless spin, calm and unfaltering. A pulsar's timing is so stable because its rotation is anchored by enormous density and immense gravity. There is nothing to slow it, no atmosphere to drag it down, no tectonic motion to disturb it, no external friction to break its stride. It turns in perfect emptiness. It spins in pure silence. Its internal structure, superfluid and rigid all at once, behaves with a precision that no mechanical system on Earth can match. But the true wonder emerges when many of these pulsars are observed together. A network of them, spread across the galaxy, can become a galactic timekeeping system. Their pulses reach Earth at predictable intervals, like signals from ancient lighthouses. Scientists track their timing to detect subtle disturbances, gravitational waves stretching space, interstellar clouds bending radio paths, even the motion of the Earth itself shifting around the Sun. Think of that for a moment. We measure our own movements by listening to expired stars still spinning hundreds of light years away. Time, in this sense, becomes a conversation between Earth and the cosmos. Some pulsars, especially the fast ones, drift in their timing by only a few nanoseconds over years. A single human blink lasts millions of nanoseconds. Yet these collapsed stars maintain accuracy far beyond that. Their rotation is not just measurement, it is memory, a record of the forces at birth, a continuation of motion inherited from a star that once burned brightly. Let your breath lengthen. Inhale deeply, exhale slowly, and imagine the passage of time the way a pulsar experiences it, not in rushes or leaps, but in an unbroken line of quiet turning. Even when pulsars glitch, jumping slightly forward in rotation, they quickly settle back into their predictable rhythms. Their errors are tiny, their corrections immediate. It is as if the star remembers how it is supposed to move and returns to that path without hesitation. This stability is used to probe the galaxy. Pulsar timing arrays can detect ripples in space-time caused by supermassive black holes merging in distant cosmic corners. The star's steady pulse becomes a ruler capable of measuring distortions a billionth of a billionth the width of an atom. No instrument on Earth alone could do such a thing. But with a star as the pendulum, the universe itself becomes the clock. As you rest here, imagine the sky filled with these soft pulses, invisible signals passing through you every moment, each one marking a rotation that began before humans walked the Earth. A quiet metronome woven into the fabric of night. Neutron stars show us that time can be steady, that rhythms can persist, and that even in collapse there remains continuity. They are reminders that not all clocks tick loudly. Some whisper across light years, keeping perfect time in the dark. Every neutron star begins with an ending. Before the quiet glow, before the precise pulses, before the superfluid core and the rigid crust, there is a moment of unimaginable release, a supernova. The death of a massive star is not a slow dimming, but an eruption, a final exhale so powerful it briefly outshines its entire galaxy. Yet within that violence lies the seed of something calm, something small, something that will endure long after the explosion fades. Imagine a massive star nearing the end of its life. Its core fuel dwindles, fusion slows, the pressure that once held gravity at bay weakens. Gravity, patient for millions of years, begins to draw inward again. The core collapses in a fraction of a second. The outer layers follow, falling inward at speeds too great to imagine. Then, impact, rebound. A shockwave races outward. Light floods the universe. A star dies in brilliance. Take a slow, soft breath. Inhale, imagining the collapse. Exhale, imagining the explosion expanding into silence. The supernova scatters the star's outer layers into space, enriching the cosmos with heavy elements forged in those final moments. But the core, crushed beyond recognition, remains. What is left after the explosion depends on the mass. A sufficiently massive core will collapse into a black hole. But for millions of stars that sit at the threshold between extremes, the final product is a neutron star, a tiny, dense, glowing relic floating in the aftermath of destruction. As the supernova fades, the neutron star is born into silence. The shockwave continues outward. The dust and gas expand into a beautiful nebula, but the core remains behind, spinning rapidly from the collapse that shaped it. In its first moments, it is blisteringly hot. Over time, it cools. The bright X-rays soften. The surface shrinks into calm. The pulses stabilize. The storm settles. What begins as chaos becomes one of the universe's most tranquil objects. Imagine drifting through the remains of a long-ago supernova, a cloud of colourful gas gently expanding across light years. At the centre, you see a tiny sphere glowing faintly, rotating steadily, quiet as an ember in ash. That is the neutron star, the last breath of a sun condensed into something impossibly small, yet infinitely resilient. There is a kind of grace in this transformation. A star that once raged with fusion becomes a calm guardian of its own past. A giant collapses into a city-sized sphere. A blaze becomes a whisper. The transition from fire to stillness mirrors the way some moments in life shift from intensity to reflection, the way great endings make room for new forms of existence. Take another slow breath. Imagine the quiet that follows great effort, the peace that lies after emotional storms. That is the neutron star's essence, stillness earned through unimaginable pressure. Over time, the supernova remnant disperses. The nebula thins, the colours fade, but the neutron star remains, spinning in the dark, carrying the memory of its birth in every rotation. It may live for billions of years, outlasting the fading echoes of the explosion that created it. It becomes, in a sense, the universe's witness, a reminder that even the brightest fires eventually become quiet. A neutron star is the last breath of a massive sun, not an ending, but a transformation. Not destruction, but distillation. A whisper left behind in the silence after cosmic thunder. Every neutron star lives close to a boundary, a threshold beyond which even its incredible density cannot hold. Gravity, the force that shaped it, the force that balanced it, the force that keeps it whole, also waits patiently for its chance to draw the star one step further. And if a neutron star gains enough mass, perhaps by merging with a companion, or by steadily feeding on the gas of a nearby star, it can cross that boundary. When it does, there is no new phase of matter, no next layer of exotic structure. There is only gravity winning completely. The neutron star collapses again, becoming something darker and more mysterious, a black hole. Imagine drifting near a neutron star perched on that edge of possibility. It spins steadily, it glows softly, its crust holds, its core flows in silence. But deep inside, the balance is fragile. Neutrons resist being crushed any further, a quantum pressure holding gravity at bay. For now, the star endures, but if even a small amount of additional mass settles onto it, the centre may no longer sustain the pressure needed to keep collapse away. Take a slow, steady breath. Inhale the tension of a moment poised at a threshold. Exhale the quiet acceptance that follows. If the mass passes a critical limit, somewhere around 2 to 3 times the mass of our Sun, the neutron star can no longer resist. The neutrons themselves dissolve. The core compresses, then collapses inward. No crust can hold. No superfluid can stabilize. Gravity folds space-time so tightly that nothing, not even light, can escape. In seconds, the star's structure disappears beyond an event horizon. A black hole is born, yet from the outside the transition is almost peaceful. There is no explosion, no outward flare, just a quiet dimming, a gentle vanishing. A star that once pulsed, glowed, or spun now becomes an invisible well in the fabric of night. And what remains? Not the shine, not the surface, but the gravity, intensified, pure, silent. Think of this transformation as a return. A neutron star already exists at the limits of physics, its matter pressed to the edge of what particles can endure. Becoming a black hole is simply the next step inward, the last possible surrender to gravity. There is beauty, even comfort, in the completeness of that surrender. Scientists learn about this threshold from the masses of observed neutron stars. Most hover safely below the limit, spinning and cooling through long lifetimes, but a few approach it, heavy enough that their futures are uncertain. Others have passed it already, merging in spectacular collisions that end not in a glowing remnant, but in a quiet singularity. Take another slow breath. Inhale, imagining that perfect balance. Exhale, imagining the moment gravity finally wins. If you could watch this transformation, though no one ever will, it would happen quickly. One moment, a city-sized star with a solid crust and intricate internal structure. The next, an object whose surface is no longer meaningful, whose density has no limit, whose interior is permanently hidden. Abdike, horizon forms wrapping around the collapse like a curtain closing gently. But nothing of the neutron star's story is lost. Its spin, its mass, its magnetic field. These are woven into the black hole it becomes, information reshaped, relocated, still part of the cosmic fabric. The neutron star ceases to be a star, yet continues as something new. In this way, neutron stars teach us one final lesson. Even endings can be beginnings. Even collapse can be transformation. Even the heaviest pressures culminate not in destruction, but in another form of existence. Where the neutron star ends, the black hole begins. A passage from one mystery into a deeper one. A quiet slip across the edge of possibility. There is a number often repeated when speaking of neutron stars. A single teaspoon of their material would weigh billions of tons. It's a sentence so astonishing that the mind recoils from it, unable to anchor the idea to anything familiar. Billions of tons compressed into the space that could sit quietly in the palm of your hand. The density is so extreme that it feels less like a measurement and more like a metaphor, a reminder that the universe sometimes hides infinity inside the smallest places. Imagine holding a teaspoon in your hand. Its curved metal bowl reflects the dim glow of your room. It's light, familiar, something you've held hundreds of times without thinking. Now imagine that inside it rests material from the heart of a neutron star. The weight would compress everything beneath it. The table, the floor, the building, the ground, as if the earth itself were made of soft clay. The spoon would fall through rock, mantle and core, carving a path straight toward the planet's centre. Its density is beyond comprehension. Take a slow breath in, letting your thoughts expand to hold this impossible image. Exhale, and allow the idea to soften into something calm and wonder-filled. In a neutron star, this density is not a curiosity. It is the foundation of existence. The collapse that forms the star squeezes matter so tightly that electrons fuse with protons, creating a vast ocean of neutrons. These neutrons, each only a fraction of a centimetre across, packed together with almost no empty space between them. Imagine a world made entirely of the interior of atomic nuclei. That is the heart of a neutron star. And yet, even with all this density, the star holds shape. It does not collapse further unless pushed past a critical mass. Quantum forces, the Pauli exclusion principle, neutron degeneracy pressure, act like invisible beams, holding the structure in a delicate balance. Gravity pushes inward, quantum rules push outward, and somewhere in the middle, the star finds a peaceful equilibrium. Strange density becomes strange stability. Let yourself picture this balance as a breath. Inhale, gravity gathers, drawing inward. Exhale, quantum pressure answers, holding firm. A quiet, eternal give and take that keeps a star intact for millions, even billions of years. The density also shapes the star's behaviour. It creates a crust harder than diamond, a superfluid interior, a gravitational field that warps space-time. Light curves around it. Time slows near it. The strange density is not just a number. It is the architect of everything the neutron star becomes. And while numbers help us describe this density, trillions of kilograms per teaspoon, 10 to 17 kilograms per cubic meter, the truth remains deeper, more poetic. Neutron stars embody the idea that the universe can compress history, pressure, and energy into a form so concentrated that it defies imagination. Think of the densest moments in your own life, times when everything felt heavy, compressed, intense. Yet somehow, within that pressure, you endured, you adapted, you found equilibrium. Neutron stars echo this resilience on a cosmic scale. They show us that even when life compresses us beyond what seems possible, a new form can emerge. Small but incredibly strong, dense but balanced, quiet but enduring. 1 teaspoon of a neutron star is too dense to exist on Earth. But in the quiet dark of space, this impossibility becomes a star, a stable, glowing remnant of an ancient sun. Infinity held in a teaspoon, density held in a moment, strength held in silence. From a distance, a neutron star can appear perfectly still. Suspended in a dark expanse, glowing faintly, it resembles a quiet ember drifting through an endless night. Yet up close, everything about it is in motion, rotation, magnetic fields, superfluid currents, drifting heat. A neutron star is a paradox of extremes, an object shaped by violence and held in perfect balance, its internal rhythms continuing for millions of years. Stillness in the cosmos is never absolute. It is simply motion stretched across long spans of time. Imagine floating near a neutron star from afar. It seems serene, almost motionless, its glow steady and unchanged. The silence around it feels profound. But as you drift closer, the hidden rhythms begin to emerge. The star spins. The crust shifts subtly under immense pressure. The superfluid interior moves with frictionless grace. Even light itself bends as it climbs out of the star's gravitational well. Take a slow breath in, imagining the hidden motions beneath the surface. Exhale into the illusion of stillness that blankets the star like a soft veil. Neutron stars rotate thousands or millions of times every year, a pace so rapid that, if we could hear it, the rotation would hum like a note of pure, steady vibration. But we do not hear it. We observe it across unimaginable distances, where the star's rotation becomes a slow, gentle repetition. One pulse a second, one flicker of X-rays, one whisper of heat. Spaced evenly, comfortingly. The rush of motion becomes the calm of rhythm. Even their cooling is a kind of motion, though we measure it over millions of years. A young neutron star loses heat quickly at first, then settles into a long, slow decline. From millions of degrees to hundreds of thousands, from bright X-rays to soft infrared. Cooling that unfolds so gradually that an entire human civilization could rise and fall without the temperature changing enough to notice. Neutron stars embody the long breath of the universe, the exhale of a giant star compressed into near eternal stillness. Now imagine the magnetic field, invisible, powerful, anchored deep within the star's core. It drifts and twists slowly over centuries, rearranging itself in patterns we cannot see. Sometimes the shifts build tension, leading to a starquake, but most of the time they remain silent, unnoticed, part of the quiet evolution of the star's identity. Inhale again, softly. Feel the way your breath slows time. Exhale, letting the idea of centuries-long motions ease your thoughts. The overwhelming density of a neutron star creates stability. Once the star settles into equilibrium, little can disturb it. It is not buffeted by wind. It is not eroded by weather. Its internal activity is balanced by pressures so extreme that they dampen chaos. It is motion held in harmony, movement without turbulence. This stillness is not emptiness. It is presence. A fullness of mass and energy held together so tightly that the star becomes a monument to balance. Even the gravitational waves emitted by neutron star pairs spiraling inward happen over millions of years. Each orbit shrinks by only a tiny amount. Motion stretched into the gentlest progression. As you lie here, imagine finding that same kind of stillness in your own life. A place where motion continues, but gently. Where change unfolds slowly, without pressure to rush. Where every breath is a reminder that stillness is simply motion seen from the right distance. Neutron stars teach us that calm is not the absence of movement, but the harmony of it. That stillness is a rhythm softened across time, that even the most intense forces can settle into grace. In the heart of a neutron star, physics reveals a side of itself we rarely glimpse. Not the tidy formulas of classrooms or laboratories, but the raw, elegant, almost lyrical version of itself that emerges only under unimaginable pressure. Here, at densities far beyond any earthly experiment, equations stop being abstractions and become living structures. Forces that are invisible in our daily world take shape, becoming the architects of matter and memory. In this realm, physics isn't just a science. It is a form of poetry written in gravity, density, and time. Imagine standing at the edge of thinking, the place where intuition ends and imagination begins. That is where neutron stars exist. Their interiors are ruled by principles that defy ordinary logic. Neutrons pack together so tightly that they form a quantum ocean. Magnetic, fields twist into shapes that textbooks can barely describe. Superfluids flow without friction. Crusts crack with energies equivalent to global earthquakes compressed into millimeters. Take a slow, gentle breath. Inhale the strangeness. Exhale into the wonder. Deep inside the star, neutrons float in a synchronized dance governed by the Pauli exclusion principle, a quantum rule that prevents particles from occupying the same state. It is a quiet law, invisible in daily life, yet here it becomes a powerful force pushing back against gravity itself. This resistance, born from quantum pressure, keeps the neutron star from collapsing further. A principle so small, so subtle, suddenly becomes a pillar holding up an entire world. Gravity too transforms into something almost mythical. On Earth, it is gentle, familiar. But near a neutron star, it is so strong that it curves space like a painter bending a canvas. Light does not simply leave the surface. It struggles, climbing upward through warped space-time, bent and delayed by the star's immense mass. If you could hover there, you would see the horizon distort, the star's surface wrapped in its own glow. Magnetic fields behave like living sculptures. They twist, tighten, and reshape themselves in ways that defy visual imagination. In magnetas, these fields grow so strong that they affect the structure of atoms, elongating them like threads of light under tension. Even vacuum, the empty space surrounding the star, becomes polarized, shimmering with quantum fluctuations, a place where emptiness behaves like glass. And all of this, the pressures, the densities, the bending of space, the shimmering vacuum, happens in silence. Physics working its craft quietly, elegantly, endlessly. Take another slow breath, letting the symmetry of these laws soothe your mind. Every breath is a reminder that order exists even in chaos, that the universe follows rules so deep they remain steady even under unimaginable transformation. The beauty of extreme physics is that it reveals how flexible reality truly is. Matter can collapse into new forms, time can stretch, space can bend, fields can intensify until they break atoms apart, and yet everything remains governed by the same foundational principles, just pushed to their absolute limits. This is the poetry, that the universe behaves consistently, even when it behaves impossibly, that the laws we learn on Earth extend gracefully into the heart of collapsed stars, that nature is not only powerful but profoundly elegant. Neutron stars remind us of the quiet sophistication of the cosmos. They show us the hidden creativity of physics, not chaotic but exquisitely structured, not random but deeply meaningful, not rigid but adaptable enough to sculpt the densest objects in existence. As you drift deeper into rest, imagine equations turning into curves of light, forces into flowing seas, quantum rules into the architecture of an entire star. In neutron stars, science becomes art, and in that art we find a new way to see the universe, not as a set of rules, but as a poem written in gravity and silence. In the grand sweep of cosmic history, neutron stars are improbabilities made real, objects that exist only because a delicate chain of circumstances allows them to be born. They are not inevitable. They are not common like ordinary stars, nor simple like planets. They arise only when the right mass, the right pressures, the right physics, and the right timing all converge in a single luminous life. In this way, neutron stars are reminders of how much of the universe depends on chance, and how creation often emerges from the narrowest paths. Imagine the life of a massive star. It forms only in regions where gas clouds are dense enough, cold enough, and quiet enough to collapse under their own weight. Most clouds drift untouched for billions of years. Only a few ever birth giants, and only the most massive of those giants, stars 8, 10, 20 times the mass of our Sun, will someday collapse into neutron stars. Already, the stage is rare. Take a slow breath. Inhale the fragility of these cosmic conditions. Exhale into the idea that rarity does not diminish beauty, it enhances it. Once a star is born, its future depends on balance, the push of fusion, the pull of gravity. Too light, and it becomes a quiet dwarf. Too heavy, and its collapse forms a black hole. But in a narrow middle ground, where mass hovers between possibilities, neutron stars emerge. They are not the most massive survivors. They are not the least. They are the children of cosmic coincidence. Even their survival of supernova explosions requires precision. If the explosion is too weak, the star collapses into a black hole. If it is too strong, the core is torn apart. A neutron star lives only when the blast is balanced just enough to eject the outer layers, while allowing the core to remain intact. A cosmic tightrope, a moment of equilibrium amidst destruction. And then, after they are born, other chances shape what they become, whether they slow or speed up, whether they shine or stay quiet, whether they find companions or drift alone. Their lives are written not by destiny, but by encounters, by environments, by timing measured across millions of years. Take another breath. Imagine your own life shaped by moments of chance, the people you've met, the paths you've taken, the choices that seemed small but weren't. Neutron stars mirror this truth. Existence is not guaranteed. It is a tapestry woven from improbabilities. The very physics that enables neutron stars requires the universe to be finely tuned. The strong nuclear force must be powerful enough to bind neutrons together. Quantum mechanics must resist gravity at just the right threshold. If any of these constants varied even slightly, neutron stars would not exist. Perhaps stars would collapse immediately to black holes, or perhaps they would fall apart before forming anything dense. The universe we know, its chemistry, its structure, its evolution, depends on these delicate balances, and yet, here they are, perfectly balanced remnants of once luminous giants, evidence that creation often arises in the narrow spaces between extremes. Imagine drifting past a neutron star now, watching its soft glow in the cosmic night. Think of the billions of years, the countless accidents, the delicate alignments that brought it into being. There is something deeply calming in that idea, that beauty can emerge from precise, improbable conditions. That existence itself is a quiet triumph. Neutron stars remind us that the universe does not operate through certainty. It operates through possibility, through moments where forces align, where collapse becomes creation, where endings become beginnings. Chance allows them to exist. Creation gives them form. Time gives them meaning. It's strange to imagine, but the universe we know, the planets we walk on, the metals we shape, the chemistry within our bodies, depends quietly on the existence of neutron stars. Without them, entire chapters of cosmic history would be missing. Worlds would form differently. Elements essential to life would be scarce or non-existent. Even our understanding of physics would be incomplete, missing the clues offered by these dense, silent remnants. Imagine a universe where no neutron stars exist. Massive stars would still collapse at the end of their lives, but their cores would fall directly into black holes, leaving no middle ground, no remnants suspended between collapse and infinity. The variety of stars in the cosmos would shrink. There would be no pulsars marking time across the galaxy, no magnetars sending bursts of energy, no millisecond pulsars whispering gravitational waves across space. Take a slow breath in, feeling the absence of these rhythms. Exhale into the emptiness of a cosmos missing its quietest clocks. Without neutron stars, the heaviest elements, gold, platinum, uranium, and many others, would be far rarer. These elements form primarily in the explosive collisions of neutron stars. If such mergers never existed, planets like Earth might still form, but their surfaces would be deprived of many essential metals. Technology, biology, even the geology of our world would unfold along different lines. Your jewellery, your electronics, the minerals in your bones, all of these contain atoms forged in neutron star collisions. Without these stars, the universe would still shine, but it would shine with fewer colours, fewer materials, fewer possibilities. Even the structure of galaxies would feel different. Pulsars serve as anchors in astrophysical measurements, allowing us to map gravitational waves, test the curvature of space-time, and understand the interstellar medium. Without them, our cosmic navigation system would be less precise, our measurements less grounded, our models less refined. It would be like trying to understand an orchestra with one entire section missing, the faint, steady percussion that gives structure to the music. Take another gentle breath. Inhale the idea of silence where pulses once were. Exhale into the stillness of a cosmos missing its hidden metronomes. Neutron stars also act as laboratories inaccessible on Earth. They let us study nuclear physics, quantum fluids, and extreme gravity in ways that no experiment on our planet could replicate. Without their existence, much of our understanding of matter under extreme conditions would remain theoretical, untested, incomplete. And there is something deeper still. Neutron stars remind us that collapse can lead to transformation, that endings can create new forms of being. Without them, the universe would tell fewer stories about resilience, about balance under pressure, about the quiet stability that follows unimaginable change. A universe without neutron stars would be simpler but also emptier, missing the strange beauty that arises at the edge between destruction and endurance. As you breathe softly now, imagine the real universe, the one we inhabit, filled with these tiny, dense stars scattered across the dark. Most are invisible to the eye, hidden in shadows, yet their presence threads through the galaxy like a quiet scaffolding of possibility. They shape worlds, they enrich planets, they guide measurements, they embody physical extremes. The universe is fuller because neutron stars exist, richer in chemistry, deeper in complexity, more expressive in the stories it tells. Their absence would leave a silence not just in space, but in the very structure of reality. For all their distance, for all their strangeness, neutron stars pull at something deeply human. They're objects we will never touch, never orbit, never approach, yet they resonate with us in a way that feels intimate, almost personal. Perhaps it is because their story mirrors aspects of our own lives. They're shaped by pressure, transformed by collapse, and sustained by balance. They endure, they hold steady, they reveal complexity beneath their calm surfaces. Imagine lying beneath a night sky, the stars scattering their cold shimmer across the darkness. You cannot see a neutron star with your eyes, not even one. And yet, the atoms in your body carry the memory of their collisions. Gold in a ring, iodine in your blood, rare elements in your brain. These are not abstract connections. These are physical links. Pieces of neutron star history woven into your existence. Take a slow breath in. Inhale the quiet understanding that you are in some small way made of their remnants. Exhale into the comfort of that cosmic lineage. There is something profoundly relatable about an object that endures such pressure and still finds equilibrium Humans too face forces that compress us: expectations, responsibilities, memories, uncertainties. And like neutron stars, we find ways to hold together, to adapt, to become something new after collapse. The resilience written into neutron stars echoes the resilience we find within ourselves. Their rhythms also speak to us. The pulses of a neutron star, steady, predictable, unwavering, feel like the heartbeat of the universe. They remind us of the comfort of repetition, the reliability of cycles, the grounding power of a steady beat in an ever-changing world. In moments of overwhelm, people often seek rhythm: soft music, calm breathing, waves lapping at a shore. Pulsars embody that soothing constancy on a cosmic scale. Let your breath fall into rhythm now, slow, steady, unhurried, as if syncing with a distant pulse in the sky. Neutron stars also fascinate us because they push the limits of what is possible. They compress matter beyond imagination. They warp time. They exist at the border between physics we understand and mysteries we still seek to uncover. Humans are drawn to edges, the boundaries where the known meets the unknown. These stars inhabit that threshold. They are puzzles wrapped in tranquil silence. But perhaps the deepest reason we feel drawn to neutron stars is that they remind us of transformation. A star that once burned fiercely collapses, not into nothingness, but into something smaller, denser, quieter, yet still astonishing. Life too moves through phases. We grow, we falter, we change shape, we soften, we strengthen. We carry history in ways that outsiders cannot see. Neutron stars hold entire lifetimes inside their calm glow. Their crusts contain the memory of starquakes. Their rotations carry the imprint of their birth. Their cores retain the pressure of their final collapse. They are quiet archives of everything that came before. Take another gentle breath. Inhale the sense that resilience can be beautiful. Exhale knowing that stillness can hold immense power. We connect to neutron stars not because we understand them, but because in some deep symbolic way, they understand us. Their stories reflect our inner lives. The pressure we endure, the cycles we fall into, the transformations we pass through, the hidden structures that help us stay whole. They are distant, but they feel familiar. Silent, but they speak to us in rhythm. Extreme, but they embody calm. In their glow, we see the poetry of endurance and a reflection of our own quiet strength. There is a quiet lesson woven into every neutron star, a lesson about how pressure, even unimaginable pressure, can create forms of strength that would otherwise be impossible. These stars are born from collapse, from the crushing weight of a dying giant. Yet out of that collapse emerges something stable, balanced, and enduring. A neutron star is not destroyed by pressure, it is defined by it, and in this way it offers a reflection of resilience that resonates far beyond physics. Imagine the moment of collapse, the core of a massive star giving way, layers of gas falling inward at unimaginable speed, gravity tightening like a fist. Everything that once made the star bright is squeezed, compacted, overwhelmed. Yet in that instant of deepest pressure, a new form emerges, denser than anything, stronger than steel by orders of magnitude, calm in its new equilibrium. Take a slow breath. Inhale the idea that pressure does not always break things. Exhale into the possibility that pressure, under the right balance, can lead to new forms of strength. Inside a neutron star, pressure forces electrons and protons to fuse into neutrons, creating a structure so stable that even the crushing gravity of a collapsed sun cannot compress it further. This transformation is not gentle, it is not peaceful, but the result is remarkable. A star that can spin for billions of years, resist incredible magnetic forces, and hold together under conditions that defy imagination. Resilience is not the absence of pressure, it is the ability to hold shape under it. A neutron star embodies this truth with every rotation. Even its crust, thin by terrestrial standards, becomes the hardest known material because of pressure. It is the pressure that aligns nuclei in rigid lattices, pressure that locks atoms into structures unbreakable by anything but cosmic forces, pressure that makes the crust capable of supporting mountains as small as grains of sand, but with the mass of continents. Take another breath. Inhale the weight of your own challenges. Exhale into the thought that some pressures deepen your strength, rather than diminish it. Neutron stars also demonstrate resilience through balance. Their structure exists at the edge between collapse and stability, between gravity pulling inward and quantum forces pushing outward. The star survives because these opposing forces find harmony. This balance is delicate but enduring, a quiet reminder that resilience often comes not from overpowering one force with another, but from finding equilibrium between them. In our own lives, resilience rarely looks like unshakable strength. More often, it looks like balance, the ability to hold opposing pressures without collapsing, the ability to continue spinning, cooling, glowing, even when the forces shaping us feel overwhelming, the ability to adapt, to stabilize, to find stillness after storms. Neutron stars glow long after their explosions fade. They continue to spin long after their fuel is gone. They persist as some of the most stable objects in the universe, shaped not by ease, but by intense transformation. Let your breath settle gently now, slow and even. Imagine that quiet glow, a sign not of weakness, but of survival. Resilience is not about avoiding pressure. It is about becoming something new because of it. A neutron star, forged in collapse, becomes a beacon. A remnant becomes a lighthouse. A moment of destruction becomes a lifetime of endurance. Their story reminds us that what feels like an ending can become a different kind of beginning. Smaller, quieter, but infinitely stronger. Pressure creates the neutron star. Balance sustains it. Time reveals its resilience. For all we've discovered, for all the signals we've captured and the theories we've refined, neutron stars remain some of the greatest mysteries in the cosmos. They sit at the edge of physics, a place where our equations strain, where our understanding wavers, where reality behaves in ways we can describe but not fully comprehend. And that lingering uncertainty is part of their quiet allure. They are stars we can measure but not truly know, objects we can study but not touch. They hold secrets deeper than their gravity wells. Imagine standing at the boundary between knowledge and wonder, the place where questions open like doorways, leading not to answers, but to deeper questions. That is the realm in which neutron stars exist. Take a slow breath in, inhaling the vastness of the unknown. Exhale softly into the comfort that comes from remaining curious. What lies in the deepest core of a neutron star? We are not sure. Theories suggest quark matter, hyperons or exotic condensates, but none can be tested directly. Our telescopes hear the surface, our equations predict the inside, but no instrument can reach through kilometers of neutron-dense matter. The interior remains a sealed world, hidden even from the most sensitive detectors. How do their magnetic fields grow so strong? We understand the basics, collapsing magnetic lines, rotating charges, but we do not fully grasp why magnetaires reach intensities that fracture crusts and twist space. The physics of magnetic field amplification at such extremes remains an open puzzle, a question whispered through the crackle of distant X-rays. How does superfluidity work at these densities? Superfluids on Earth are delicate. They form at low temperatures in controlled environments. Yet in neutron stars, superfluidity survives crushing gravity and intense heat. It shapes the star's rotation. It drives glitches. It affects cooling. But the details, the exact structure of the superfluid, the behaviour of vortices within it, remain shadows in our models. Take another gentle breath. Inhale the humility of not knowing. Exhale into the idea that mystery is part of exploration. Even the formation of neutron stars raises questions. Which stars leave behind neutron cores? Which collapse to black holes? What determines the boundary between them? The threshold depends on mass, rotation, metallicity, and perhaps conditions we have yet to imagine. And every new observation shifts the line slightly, like a tide that never fully settles. And then there is the biggest mystery of all. What happens when matter is pushed past the neutron star limit? When collapse becomes inevitable, but physics has not yet revealed its final shape. We know the result, a black hole, but the transition itself remains hidden behind horizons we cannot peer through. In the face of these unknowns, neutron stars become reminders that science is not a collection of facts, but a conversation with the universe, a dialogue that continues through pulses, glows, waves, and uncertainties. Let your breath steady now, slow and deep. Feel the space that mystery creates, a quiet place where curiosity can rest, not in urgency, but in peace. We do not know everything about neutron stars. We may never know everything. And that is part of their beauty. They remain just slightly out of reach, like a dream that lingers at the edges of memory, close enough to sense, distant enough to wonder. They are cosmic puzzles wrapped in silence, waiting patiently as we refine our questions. And in that waiting, in that mystery, we find a kind of calm, the comfort of knowing the universe still holds secrets worth drifting toward. In the vast timeline of the universe, neutron stars are not fleeting sparks. They are long-lived, enduring remnants that persist through eons, long after their supernova explosions fade, long after their pulses slow, long after their magnetic storms settle. They drift into an age of profound quiet. Their evolution becomes subtle, stretched across billions of years, a kind of cosmic twilight that unfolds so slowly it resembles eternity. Imagine a young neutron star, fresh from the explosive birth of a supernova. It spins rapidly, it glows fiercely, it radiates energy with a kind of youthful urgency. But as time passes, the spin decreases, the heat fades, the magnetic field relaxes. What was once intensely bright becomes a soft ember. Take a slow breath in, imagining that ember cooling. Exhale as it drifts into the long calm of stellar aging. After 1 million years, the neutron star has cooled enough that its X-ray glow becomes faint. Its pulses continue, but more slowly. Its magnetic field still reaches far beyond its surface, but with less force. The star is no longer a lighthouse, it is a lantern, quiet, persistent, knowing. After tens of millions of years, the cooling deepens. Thermal radiation fades into the infrared, then becomes too weak for most telescopes to detect. The crust settles. The superfluid core moves with timeless grace. Glitches become rarer. The star's rotation slows into gentle, almost meditative repetition. These changes are not dramatic. They unfold like the slow settling of sand at the bottom of a still pond. Take another breath. Inhale patience. Exhale into the rhythm of time stretched to cosmic scales. After billions of years, the neutron star approaches what astronomers call a black dwarf state. Not a black hole, but a star so cool and dim that it emits almost no detectable light. It becomes a silent monument to its own history. Dense, balanced, unchanged except for the passage of time. And yet, even then, the neutron star is not truly inactive. Its gravity continues shaping its surroundings. Its presence influences the motion of nearby stars. Its residual heat continues drifting outward as an almost immeasurable whisper. Its magnetic field, though faint, endures. Nothing about a neutron star ever fully dies. it simply softens. Picture this final stage, a small, cold, nearly invisible sphere adrift in the darkness between stars. Not forgotten, not empty, simply quiet. As the universe expands, ages and cools, these ancient neutron stars remain. Long after galaxies collide, long after suns exhaust their fuel, long after planets crumble into dust, neutron stars endure as some of the last shining artifacts of stellar evolution. Their spins may slow to a crawl, their temperatures may fall to near absolute zero, but their density, their structure, their essence remain. It is possible, even likely, that in the far future, when the universe has grown cold and diffuse, neutron stars will stand among the final witnesses of cosmic history. Silent, dense, timeless. Let your breath soften now, slow and deep. Imagine the universe in its distant future, filled with nothing but quiet remnants drifting through endless night. And among them, neutron stars. Tiny, calm pearls of gravity, floating unchanged. Their lives teach us something profound. That endurance is not loud, that longevity is not bright, that the deepest forms of persistence unfold slowly, quietly, in stillness. Neutron stars move through their futures the way we drift into sleep, slowly, gently, relinquishing light, but never losing the structure of who they are. Endurance in silence, strength in stillness, existence measured not in brightness but in time. We have wandered far tonight, from the collapse of giants to the quiet glow of remnants, from magnetic storms to superfluid oceans, from pulses that mark time to silences that stretch across billions of years. And after exploring these strange, beautiful objects called neutron stars, we now drift gently back to the place where we began, the quiet question of what it means for something to endure, to transform, to hold its shape after immense pressure, to find balance after collapse. Imagine once more a neutron star hanging in the dark, small as a city yet heavy as a sun. It looks calm from afar, serene, a faint sphere of light in deep space. But now, after our journey, you know what lies inside. The rigid crust, the superfluid core, the exotic matter, the magnetic storms, the cooling glow. You know that beneath its stillness lives a tapestry of motion, memory and physics at the edge of possibility. Take a slow breath. Inhale the full circle of this journey. Exhale into the soft feeling of having travelled far, yet returning to yourself. Neutron stars begin in chaos, in explosions, collapse and extremes. But their lives afterward are defined by quiet endurance. They settle, they stabilise, they cool, they pulse softly, they find a long, patient rhythm that outlasts almost everything else in the galaxy. They remind us that beginnings can be violent, but futures can be calm, that pressure can create strength, that endings can reshape themselves into new forms. In their story, you might sense an echo of your own. Times when you've experienced pressure so deep it felt impossible. Moments when the world seemed to collapse inward. Times when everything you knew about yourself shifted, and yet somehow something within you held. Something settled. Something cooled and steadied and found a new rhythm. As you breathe now, slow and quiet, imagine that calm settling into your own life. A crust forming where you need protection. A superfluid core flowing where you need softness. A pulse of steadiness where you need rhythm. Neutron stars are extraordinary because they survive contradiction. Dense but delicate, silent but powerful, small but immense, still but filled with motion. And in that paradox they resemble the human experience more than one might expect. You too contain many layers. You too hold pressure and light, memory and endurance, silence and motion. Your life, like a neutron star's, is shaped by forces seen and unseen. Take another gentle breath. Let it fall naturally. Feel the weight of the day begin to soften. Feel the complexity of who you are settle into simplicity. the way a star settles into its long, quiet afterlife. Now imagine drifting slowly away from that distant neutron star, watching its glow shrink into a soft ember, watching the darkness widen around it. The journey ends not with answers, but with calm, the kind of calm that comes from understanding just a little more of the universe, and in doing so, understanding a little more of yourself. You have floated through collapse, rotation, cooling, magnetism, exotic matter, and cosmic time. You have drifted through extremes and returned with a sense of stillness. Let that stillness follow you now, gently into rest. Because even in the depths of space, even in the lives of the strangest stars, everything moves toward quiet. Everything seeks balance. And now, as this voyage comes to an end, let the calm of the cosmos settle softly around you. Everything flows, sleep in that motion.